Welcome to another coding session. I'm Marcel. I'm creating a new programming language called Plum. It looks like this. I'm not going to go into too much detail about the syntax right now. You can watch the previous videos for that. Yeah. Last time we basically refactored parts of the compiler pipeline. So let me maybe show you how the pipeline currently looks. Yeah, the compiler, like most compilers, is organized into stages. We start with the source code, and then that is converted into some data structure representing the lines of the file according to their indentation. And that is passed into a syntax tree, that is passed into a graph of expressions, that is converted into a type-checked variant, the yogurt. And for a long time, we just converted that type-checked thing into C code, which was easy to do because C has the same abstraction level. So you also have data structures and you can call functions and stuff like that. But over time I want to allow creating and compiling new code on the fly while the program is running. And to do that, compiling to something and then using like GCC is not possible, or like not viable at least. So in the long term I want to replace this down here with an interpreter, and in particular a stack-based interpreter. So this is what we had for a while, and that worked. But the interpreter was quite high level, so it operated on objects, like values in the semantics of Plum. These objects were things like numbers or structs with fields or enum values, stuff like that. And to make it easy to, for the one part, create new interpreters later on in other languages, but also to make the code more performant, we don't want to have these rich but also heavyweight objects at runtime, but instead something simpler and data-driven. So I adjusted the interpreter to be to work on individual bytes and memory instead of on objects. So now the interpreter looks like this. We have this VM struct for our virtual machine. It has a data stack, which is just some bytes, and a call stack, which are addresses that point to instructions. And instructions are things like pushing a byte to the stack, or pushing 8 bytes at once to the stack for efficiency reasons. But there are also instructions like add 2 64-bit numbers. And this will pop 2 numbers from the stack, add them, and then push the result to the stack. So yeah, there were the typical like arithmetic instructions and bitwise instructions, but also memory stuff like allocating memory is also something that the VM supports. Right. Yeah, I think 2 sessions ago we implemented the VM for this, and last session we introduced another compiler stage, the Waffle, which goes in between the type-checked yogurt and the bytecode. We also implemented this part, like converting the Waffle into bytecode, which was quite difficult, as it turned out. So converting something from a graph-based representation with lots of IDs to something stack-based is kind of difficult for us humans to wrap our head around. And the only thing that remains is this part, converting yogurt to Waffle. And that's basically what I want to do today. And then, theoretically, the entire compiler pipeline should work again. So let's maybe have a look at yogurt and Waffle. The yogurt compiler stage, as I mentioned, is typed. So we have a concept of, that's in a separate file, I think. Yeah, for type. Plum has structural typing, so types are things like primitive types like ints and strings for now, but also structs and enums. And you can see a struct just has fields, which are strings, and each field has a type. And an enum has variants, which also like referenced via strings, and each variant can have multiple payloads. The way that looks in the code is, hang on, that you have something like this. So this is an enum called list, generic over some type t. And this pipe here indicates that this is an enum type, which is either empty or more. And if it's more, then it also contains a concrete t as well as the rest of the list. So it's a recursive type, which we can also see here. So we also have recursive types, which basically start a few types up in this tree. So every type is just this, which is a tree because it can contain itself. And we can't use infinite trees for recursive types. So this is basically, once you reach this recursive marker type, the int tells you how many levels above this should we start, or should we continue. So basically, if you have a recursive type, you can traverse down into that, even like to infinity basically, and it basically expands at the bottom. Yeah, right. All of the type casting algorithms, type matching, type solving, and so on. We already did all of that. And the yogurt contains, let's see, it contains expressions that each have a type. So let's maybe go through the yogurt from top to bottom. So a yogurt has functions. These are top-level functions in the file. And each function is referenced by the signature, which is basically just a wrapper around a string, but it contains basically the function name and the types of the arguments, because we also support overloading, so you can have multiple functions with the same name, but they take different types. And each of these signatures maps to a yogurt fun. A yogurt fun is defined down here. It has expressions, but these are not actually the expressions contained inside the function. They are, but they are just a global list of expressions, of all expressions that are somewhere inside this function. And the way these expressions are ordered is determined by this yogurt body. So the yogurt body down here has some parameters, which makes sense. A function can take parameters. And it has expressions, which are just yogurt IDs. And yogurt IDs basically index into this expressions slice. So the function at the top level has just a huge list of all expressions that are in the function. And those expressions then contain yogurt IDs, and bodies also just contain IDs for the expressions that they contain and also what they return. And that makes it easy to, if you are deep in some nested body in a function, because bodies can be nested, for example, switch contains bodies for the cases. If you're deep in a body and you want to reference an expression that is in some outer body, for example, then you can just save the ID, and all of the analysis steps and so on, they can easily resolve the ID using this global expression. So basically having this global function global list of expressions is more easy than actually having the expressions contained in the body and so on, because then we can easily look up expressions later on. Okay, yeah, should maybe talk about the operations that we support. So there are parameters. There are expressions which are uninitialized. For now, this is not really used unless in edge cases, like There's this never type, which basically says, hey, this expression will never finish evaluating. For example, an infinite loop, or return 5. And that means that you can use an expression of that type as anything. Yeah, we have comp time values, because at the yogurt we already did like some constant folding, which means we can also like build structs at compile time, build values, any values at compile time. Yeah, and you can see that like each value has a type and a kind, and this kind is either an int, a string, a struct, tag, which is like an instance of an enum, containing the variant and the payloads. The value can be a lambda, and it can be a type, because there's a built-in function type of that basically gives you a first-class type value, which you can then later inspect. But that's like a different story. Okay, yeah. Something else. Oh yeah, here, this expression contains the yogurt operation, yogurt op, and a type. And the yogurt op is actually what we saw down here. So that basically tells you what should this expression do when it is evaluated. All of the expressions, they are not nested. So structs, for example, they don't contain expressions or something as fields, but instead they just contain yogurt IDs, which means to create a struct, for example, you would first create expressions for the fields, and they are actually like evaluated in the order that you have them in some body, and then you can have a struct expression that aggregates those other expressions into a struct. Yeah, member accesses a struct field basically. Tag creates an enum, like I guess a tag, a value in an instance of an enum. Yogurt switch is a switch on some value, which has to be an enum. Yogurt lambda is for lambdas or closures, or however you might call them. Yogurt lambda call calls some lambda. Yogurt call calls a top level function. These are different because top level functions, they contain signatures because they have overloading and so on. Lambdas don't. You pass them around as values, and you can't, for example, have any overloading with these. Right. Yeah, instruction is the last puzzle piece of this. That contains an instruction, which is basically the built-in stuff that the VM needs to be able to do, like adding numbers or subtracting them, or for example, concatenating strings. This is something that you can't implement in the language, but these are the things that the language provides to you. So that's the yogurt. And the other part, the thing we want to compile to, is the waffle. I should... Oh, yeah. The waffle looks like this. So here there are no longer types. Instead, we have expressions, and each expression is just some memory region. So for example, here we have this basically like a struct, I guess. And this is a field access on that struct. In the Plum code, it may look like this. So there you can create structs using this ampersand, and this creates a struct with two fields, x and y. X is some integer that you got as a parameter, and y is 42. And here you access that struct. And in this representation, we no longer have any types. So this right here is just more like an aggregate of, first there was this memory, and then there was this memory. So these are just 16 bytes of memory, basically, without any semantic information of, like, this is a struct with these fields or something. And you can see that when we access the y field, you don't see y anywhere in here. instead you just access the member at offset of 8 bytes. So a word is 8 bytes, and each int is also 8 bytes, which means that this struct will contain 8 bytes representing the x, and then 8 bytes representing the y, aka 42. And this basically skips the first 8 bytes and instead only refers to this memory region, I guess, memory part. Unlike the yogurt, the expression here can also be nested. So in the yogurt, this would probably look like you have a comp time expression for or like a parameter expression, I guess, then a comp time expression of the integer 42, and then you'd have a struct expression that maps x to expression number 0, which is the parameter, and maps y to expression number 1, which would be the comp time value of the 42. In here, expressions are nested directly, so this aggregate thing here just contains the other expressions. And enums, for example, they are also represented as just memory regions with aggregates. And the way that works is that for each enum variant, we basically put a unique byte at the end of this. So, we want to, in this case, have basically a maybe enum, which is some int or none. And the way we represent that is we look at the payloads of these. So the sum variant has one payload, an integer, and the none variant has no payloads. Then we make them all the same size, basically, and put a byte after that. So the sum variant, for example, is represented as this. So in memory, 8 bytes for the actual number, and then 1 byte for the enum tag, where 1 indicates that this is the sum variant. And the none variant is actually just 8 bytes of padding, and then 1 byte that represents, that this is none. And these have to have the same size. That is why there's padding, because, well, when you work with this enum thing, regardless of the value, you want to, for example, be able to store an enum in a struct or store an enum on a stack as a local variable. And there we need to know the size of these things, regardless of the runtime value. And when you switch on an enum, you just look at the last byte, and then you know how to interpret the front part of the enum. Right. So the question is basically, how do we map this typed representation into this? And that's basically what I've been struggling with for some time. Okay, let's maybe quickly look at the type definition of this. So Waffle, just like the yogurt, contains functions. And these are probably the same signatures, I guess. But the Waffle functions are different from yogurt functions because they can have local variables, which are actually like referenced using IDs. And those bodies, they don't have parameters anymore. So in here, each body has parameters. The top level function body took the function parameters as parameters, which makes sense. And these inner bodies in the switch, they took the payload of an enum as parameters. In here, we don't have that. In the Waffle, we just have like local expressions that should be evaluated, and afterwards a Waffle body, which, it's similar to how it's done in the yogurt, that we have this basically global list of owned Waffle expressions, and the body only contains the IDs of the expressions that should be evaluated, and afterwards an expression that should be returned. Right, expressions don't have a type like the expressions in here. Here they had the actual log operation, or the expression kind, and a type. In here, they still have the kind, but not a type, instead size and alignment. So the question is, how do we map? What do we do with our types? You know, basically, we need to map every yogurt operation, I guess, or like every yogurt expression into a waffle expression. Yeah. Okay, so in the main file, let's actually just uncomment the compiler pipeline until the yogurt. Oh yeah, this is a quick little test waffle that I created that has a function called a, which just returns 42. And then there's a main function which returns a struct with 1, 2, and the result of calling that first function. I'm gonna just comment this out, I guess. Yeah, we don't care about bytecode yet, so let's just say waffle is yogurt to waffle. Nice. For the previous compiler stages, we always had this or error thing here to do error handling. Because there could be syntax errors in the file, then we would get an error here. Or there would be, you know, some unresolved names, then we would get an error here. Or there were some functions that, like, you know, you call a function, but no function matches the argument types. Or there's a type error in your program, then you would get an error here. But once we have the yogurt, like our entire program is type checked, we know that the program is correct. So toWaffle should not actually return a result, but it should return a waffle directly, because nothing can go wrong at this point. Yeah, let's move the print up here as well. Similar to the other stages actually. Okay, waffle. And yeah, then the waffle. Beautiful. Okay, yeah, so writing this toWaffle function is the task for today. For the previous compiler stages, we always had, you know, the to function in the corresponding file for the stage. So for example, the toAgg function was in the egg. And I'm gonna do that similarly here. So in the waffle file, we will have a new function, toWaffle. Takes the yogurt, returns a waffle. Beautiful. And now this down here should compile. Beautiful. Yeah, let's just run that and see that this fails. Okay, so this compiles the compiler, and now it runs the compiler, and here we see that that it passes the source code into this, and then wants to convert that to waffle, and fails. Yet the compiler is hard-coded to compile this file. So let's maybe put something interesting in here. Let's maybe say, I mean, this is actually fine, right? We just we create some enum, I guess, and then we return 0. I mean, sure. Yeah, let's compile this first. So in the waffle, the end result should be waffle, which contains functions. And the functions will probably have to create them. That's a map from waffle signature to waffle fun. And then for each function in the yogurt, I think every function just maps to a waffle function directly. I think. So this will actually be something like this. Funds put the waffle signature. Where the string is fun.signature.string. And then the waffle fun, which will just be fun.value, which is a yogurt fun dot to waffle. Okay. Maybe add a little comment to separate this out from the printing and so on. Converting yogurt to waffle. Yeah. And we also add a function for converting a yogurt fun to a waffle fun. Okay. And this looks cool. Yeah, that should be the key string. Oh, it doesn't have that. Still interesting. Sure. Nice. Yeah, can we put that on the same line? Oh, okay, sure. So, yeah, we just map all functions. That's actually surprisingly simple. So, can we do that independently? I think so, right? Because for a function, there's like sure it can call other functions, but the signatures stay the same. And like from each function, you know the types of the parameters and the return type, and that's all you need to, determine how what the stack should look like and so on. Okay, so we can compile every function independently. That's pretty nice. Yeah, so creating a waffle fun. Yeah, we need locals, which will be a slice of waffle expressions. And we probably need a body, yeah. That's going to be a waffle body. And the waffle body then, again, contains locals, I think, and stuff like that. Hang on, actually I think we created some helpers for that. Let me just uncomment this code to get syntax highlighting. Here we have the signatures. Oh yeah, and here we have a function builder. Yeah, this more complicated example. We can create a waffle fun builder, which takes, oh, I'm not actually sure what this means. 01. Something. And then on that function builder, you can define local variables using .local. And then in the end, you can call .returns to get a body. And then on the function builder, you can call finish with the body to get the actual function. Okay. Yeah, we'll probably do something similar down here. So creating a waffle fun builder. Waffle fun builder. Oh, args size. And args alignment. Okay, so basically we need to know, laying out the arguments on the stack, what is their size. Okay. I think we need to get into memory layouting again. Something I started a bit a while back, but it wasn't quite working out. But now we have like concrete things we want to do. So we need to map types to these Waffle expressions. These. And we need to do that in a consistent and predictable way. So for example, types are just a map from string to some type, some other type. So the type of this would be basically, and with x being an int and y being an int. But in the map, there's no ordering. It could just as easily be represented as this. Like these are the same type. Whether x and y, like the order doesn't matter, basically. And the question is, how do we map that to a memory layout that is deterministic based on the type? Yeah. So I guess we need to decide in which order do we put the fields in memory. And for enums, for example, we need to decide which byte represents which variant. And we need to do that so that when creating a struct, we can lay out those, those fields based on the order that we chose. And when interacting with a struct, aka getting fields from that, we need to know at which offset the members are. And for enums, similarly, when creating an enum, we need to know the size of the layout of the individual payloads, I guess, and which tag represents which enum variant. And when switching on an enum, we need to also know what does each enum variant do, like what kind of tag corresponds to which variant. So the way we did that is that we have this memory layout, which again has a size and an alignment. And it has a memory layout kind. Interesting. Sure. Memory layout kind, which is a struct layout or an enum layout. And these then have mappings from and to fields to things. Yeah. So let's maybe go through the yeah, I think this makes sense. The information that we have in here, I think we might need to change that. Because we need this, when accessing a field from a struct, we need to know the offset. But field to layout, I'm not sure we need that. Or fields sorted by offset. I think in a struct we may have padding in there. So yeah, I won't explain alignment another time, but watch the last video, I guess, the last session about padding in structs. Yeah, so maybe when creating a struct, we may need some the individual parts of the struct that we need to put in memory, maybe. And that will just be a slice of struct parts. Yeah, I think that's better. And a struct part is an enum that is either a field with a string, and because every field has a type, we also know, you know, the layout of the type. You can get the layout of types. Or it can be padding. So basically this will be, you first put this field in here, then put some padding in there, then put this other field in there. You could represent this as this. Yeah. So now this struct basically contains the information that we need to construct a struct by telling us which parts to put in memory, and then also to deconstruct a struct by telling us like which field we can access at which offset. For enums we will do something very similar. Yeah, we will have I'm not sure. I think we will just have parts, which will be a slice of enum parts. Yeah. And we may have, like, yeah, I think this belongs in this layout thing. Like, you know, tag offset is in it. Tag offset, and also probably this, like num to variant and variant to num. Does that make sense? Yeah, I think so. Yeah, let's just put that in here. We don't need this. And yeah, enum parts. So that can also either be padding, or it can be basically a payload argument of some index. Oh yeah, and by the way, this should be a map from variant to layout, I guess. Oh, hang on. Variant to slice of that. Yeah. And then there's a tag, which is an int. Like this directly contains the value. Okay, yeah, I think I like that. Yeah, this that we don't. Oh wait, we might need this. Yeah. Let's maybe put that in here as well. So arg offsets, basically for each variant, we know the offsets that the parts, the arguments are at. Okay, yeah, I think that is reasonable so far. I'm just gonna comment comment this out for now and instead put a to-do in here. Yeah. Okay. And just use that over here. Maybe add something to the to-do, like okay, so yeah, converting yogurt to waffle means that we have the arguments. We basically want to lay them out. So fun dot param. Hang on, let me see what these are. It's a slice of yogurt IDs, right? Because the function doesn't have parameters directly, but instead the body has parameters. Let's see a function body param. Let's maybe just gather all the argument types. Yeah, argument types is I guess a slice or like a list of types. And for every parameter in these params, we basically get the type of that parameter. Oh, hang on, this is just an ID, right? So we need to get the actual expression from the function, get the parameters type, and then we push that to the argument types. Like this. Nice. Now we have all the argument types, and I think we can just, we should choose a memory layout for them. Okay, yeah. Something like this is what we're going to need. So on a slice of plum types, we should be able to call memory layout, and that should return us a memory layout of basically laying these out efficiently. Basically what we have down here. Yeah, let's just call it memory layout. Oh, it's a slice of So maybe we need something like memory layout types. Like I don't know the types of, like the memory layout types that we need. This is a rough guess of what we might need, but I think I'll just write down the Waffle compiler, like you know, yogurt to waffle, and just pretend that the memory layouting exists, and it returns something that has the things we need. And I'm just going to fill out this struct, for example, as I use it. And then when all of that is done, then we can go back to this memory layout file and look what API just naturally emerged. So yeah, this will just be a to-do for now. And this should return us a memory layout for the parameters. So param layout. Beautiful. Okay, then this will be the param layout size and alignment. which means this will need a size and an alignment. Okay. That's cool. Then we build the body by saying, hey, we want a body. And we build local variables. So I think initially we'll just map every yogurt expression into a local variable. So for expression in, I guess, fun dot body dot expros, something like that. We basically say builder dot, hey, please define a local expression. Expression to waffle, something like this. Yeah, to waffle is not a field on yogurt ID, that is true. But hang on, let me maybe get the expression from the body. So to waffle should return a waffle expression, I think. Taking a yogurt expression. So we map each yogurt expression that we get into a waffle expression. Builder.local creates that. And right in the end we say builder.returns with a waffle expression. And I think here we can just, I think the body, like the function dot body, has a returns thing, which is an ID. Oh yeah, yogurt ID, but we need a waffle expression. Yeah, so let's maybe also keep a mapping from yogurt ID to waffle expression. Something like this. And then when we do, when we do this, then here we do this. Like this is the waffle expression, and then we say yogurt ID to waffle expression. Yeah, this is not, like this is actually an ID. And we do something like this. Okay, yeah. So now we know what waffle expression this maps to by just looking it up in this map. Okay, and then we finish building the function. That looks fine. Okay, next problem: how do we map expressions? And I think yeah, we need the mapping here as well. So not mutably, but we need to be able to refer to previously defined expressions. Like this. And let's, oh yeah, that means that in here we need to pass in this map. Okay. And the question is, what do we do in here? And I think we'll just switch on what kind of expression this is. And my voice is giving out. Oh man. Yeah, let's just copy this enum over here, and then let's turn these into switch cases of stuff. Yeah, for parameters, this should be unreachable because they can never occur in a body. They can only occur at the beginning of a function and in switches, and there we should treat them separately. Okay, uninitialized. Let's just put unreachable here. I'm fairly certain that will come back to us, but meh. So yeah, converting a value, like a yogurt value, to a waffle should also be a thing. Yeah, yogurt value is like a comp time value, and that needs to be represented somehow. Okay, so we have that. Yeah, if we have a struct, which is a map from string to yogurt ID, so we want to create a struct, then I think we'll just use the Waffle struct constructor to create I think like this has nothing to do with the actual like struct type. This is just memory with several things next to each other. So I think in the long term it makes sense to maybe rename that to aggregate or something like that. I'm just gonna write that to do rename to aggregate. Sure. Okay, and yeah, we need to lay out the struct. So expression.type.memory layout. The type should be a struct type. So let's maybe just save that. And then for every... Oh, now we want to construct the struct. So for every part in the layout parts, we just, you know, do stuff. And we create a Waffle struct with, I think, fields, yeah, which is a slice of Waffle expressions. I'm gonna call them parts because that's a better name. So parts dot push. Well, and depending on what kind of part the struct layout wants, you know, if it's a padding, for example, of some amount, then you just have waffle padding in there of that same amount. And if it's a field with a name, then it like actually will just have this right here, yogurt ID to waffle expression of that field name. And yeah, the struct is a mapping from field names to the ID. So we can get the value that should be in this field using this. This is the yogurt ID of the yogurt expression that should be in this field. Yeah. And then we map that yogurt ID to a waffle expression. Yeah, okay, we can do this in line. And we have a waffle expression. Right. In the end, we create a struct of the parts. Cool, member of a yogurt member. Again, we can just get layout of the surrounding of thing. So remember that of should be a yogurt ID, and then we can get the function from the, well, we need the function. we memory layout that type. That should be a struct. And that means that we should be able to do layout dot offset of field member name or something like that to get the offset. And then we can do waffle member. Yeah, of yogurt ID to waffle expression dot get member of, which will be an ID. And what does waffle member expect? Probably the offset, size, and alignment. That's a lot of stuff. Okay, so this will be like struct layout, and then we also have field layout, which will just be the expression type memory layouted. And then in here, yeah, let's maybe do that in line, I guess, like this. Nice. Yeah, creating an enum, which will be a YogurtTag, which has, I think, a symbol and other stuff. So again, you get the layout of its type. Yeah, and then we'll build an aggregate similar to this up here. Like actually, yeah, we know that this type is an enum. So for each of the parts that this enum requires, we'll do stuff. And the memory layouting enum things, it can also have padding. Enum parts. You can have an argument and an index and a tag. Okay, so I guess let's move padding first. An argument at an index, which will just be tag.args.get index that returns an ID, a yogurt ID, and then we get the waffle expression. Okay, and then we put those into that. But we also need to handle like tags, which will just be a waffle byte, I think. Okay. Next up, switching on something. So switch has a condition, I think, which will be an ID. We can get the corresponding expression. That's its type, which will be an enum type. Memory layout that type, and then we get a layout, and that layout should have a tag. So tag offset, and we can get the member of that. So basically waffle member, we have a value of that enum. We get the tag, should have a tag size and tag alignment, I guess. I don't know. And this gives us an enum tag, okay. And then we should do a waffle switch. Is there a waffle switch? Yes. Of a byte and cases. Sure. And the byte will be this. I mean, for now, every tag is just one in size. So let's do that. And the cases, well, they are kind of a bit more complicated. So hang on, this will be a slice of waffle bodies, I think. Like a list of that. And then for each basically mapping, like this needs num to variant. Yeah, I think that for you know what, let's turn this into a map. That's a bit more, that's a bit easier. Not from byte, because round. Yeah. The entry.key will be a byte. Oh. Yeah, let's do it like this. We have an uninitialized slice of the length variance, maybe. Yeah, okay. This will be a byte, and then we can say cases dot set that index to a waffle body. So we need to take the variant, which will be a string, get the corresponding yogurt body, convert that to waffle. Something like this. Yeah, lambda, I'm not sure. Let's add a to-do in here. Similarly for lambda calls, and just for normal calls, I guess. As well as instructions. Okay. Yeah, there will probably be errors here. Exactly. True. So here we know that this is a struct type. Is there like the type thing has a struct? Okay. How would we do that? I guess we could just Yeah, I think let's add a few specialized functions maybe. Because I think this doesn't really make sense. Like, we don't do this kind of thing. We always know whether we are working with a struct or with an enum or so on. So let's maybe only have a few, like memory layout struct. And we basically assert that this is a struct. So like this. Yeah, okay. That's cool. And oh yeah, then here we can just return a struct layout. And I think similarly you'll have memory layout enum of some plum type, which will return an enum layout. Yeah. And also memory layout args, params or something. Yeah. Which with this slice of plum types. Params or args? Until now, I just, like, params are basically, they reference the same thing, but params are the slots basically that a function expects, like from the point of view of a function, and the concrete values that you pass in when you call a function, those are the arguments. So the moment that you call a function, the arguments you pass in, they become the parameters of the function. That's like how the terminology works. Yeah. So I think params is better in this case. So we'll return a params layout. Beautiful. Which will be something. Okay. And we don't need this general memory layout thing. That doesn't really make sense. That's amazing. Hey, I'm gonna move them down here as well, so we only have, because they're basically independent from each other, you know. And then we can even have sections in here. We can say like layout function parameters. Boom, one section for that. Layouting struct fields, layouting structs, layouting structs, layouting enums. And yeah, I'm probably gonna add a description for each of these once I implemented that. But I think like the general realization of let's have specific layouting calls instead of one memory layout of a plum type, like that doesn't make any sense or any you always know what kind of type you're dealing with, so you can just call the more specific ones and get actually like semantically interesting things like what are the field offsets and so on. On for an enum, where's the tag, and like that's what you actually need. Okay, yeah, I'm not gonna, no, this is all just, I'm gonna comment this out. Because that's, basically when developing, it is often common to work with, to make the small things first, like the leaf nodes basically. And that's basically what we did with the compiler. I want to replace the backend with something custom. So I first built the bytecode based VM, and like actually implement the VM instruction definitions and then the VM underneath. Then built the Waffle on top of that, and converting that. And now we're basically connecting these layers instead of going the other way of lowering things over time. And the reason I did that was because I was pretty sure what kind of VM I want to end up with. And I wasn't quite sure about how I'm going to map these. And it's very similar with the memory layout. I don't quite know, I can define some memory layout structs and enums in a vacuum, but basically these are just helper classes for this conversion between these compiler stages. The memory layouts themselves, that's the only purpose. They don't have like a separate right to exist. And there's no, a memory layout should just contain what is useful for the one who needs this layout. And that is why I defer implementing these and instead focus on converting Yogurt to Waffle first. Flesh out all of the details, all of the API that we need from the memory layouting. And once that is done, then we can focus on the memory layouting. And that's a bit like backwards from, instead of finishing this small independent thing first, the memory layouting, and then using that memory layouting somewhere, we're doing it the opposite way, where we basically implement that thing that depends on memory layouting without memory layouting itself being implemented. But it makes sense in this case, I think, because the API is unclear. And like in this case, for example, I would have, and initially I wouldn't have thought about like having separate functions for memory layouting, structs and enums or so on, but just have a memory layout this type, please. But actually when using the memory layouts, we always know which kind of type there is. And in fact, we need to, like for the struct, we need those struct-specific things about the memory layout. So I think the order in which you develop things, they like greatly affect the API services and the abstractions that you build up. So it makes sense to basically plan a bit ahead and defer those things where you are not quite sure about the API, defer those until later, and just focus on implementing the things where you're pretty sure about how they interface with the rest of the code base. Right. But like that's my reasoning behind the like meta strategy of in which order do I implement things in this session. Okay, yeah, so enough derailment. This is the signature. Yeah, the parts, I'm going into a slice. Sure. If we have a member, then we know that this will be a struct. And the field, okay, so this is interesting. For the field, we don't care about whether that's, that's a struct or enum or something. We just care about its size and alignment. So we do need basically like a general function, like this one. Layouting. Layouting arbitrary types, I guess. Yeah, that has a memory layout here. That's just gonna have a size and alignment, like the common denominator among all memory layouts. Okay, yeah, fun doesn't exist. But we need the fun here, yeah, because to convert an expression into Waffle, we may need to know the size of the other parts. Hang on, but we don't. I think we don't, because oh yeah, we do. Yeah. Like here we can kind of get around that. Yeah, we don't just need the size and alignment of the entire struct, but we also need the specific mapping from like offsets of the fields and so on. And we can't get that from these Waffle expressions because they don't contain types anymore and any information about types. We can only get that from the yogurt. So we're going to pass the yogurt fun as an extra parameter. And yeah, so layout is not in scope. That's true, because this should be the struct layout. Yes. Offset of field. And we can take, do we want methods for that? Or I think just using these fields is fine. field to offset dot get member name. Beautiful. There are no definitions. Okay, never mind. So creating a tag. This would be, yeah, memory layout enum. And then we have these parts. Nice. Layout. So the memory layout enum, the enum has parts, true. Oh, and each part will be a slice, that makes sense. Okay, so here we basically want to part. Yeah, I think we need you know what, let's call them payload parts, I guess. Yeah. Also, like, terminology, payload versus args in enums. Difficult. Yeah, but I think these should only contain the memory layout of the actual payload and not of the tag. And the tag is like separate. The tag has, I mean, the tag is always just a byte, so. Okay, so yeah, payload parse get our payload, like the you know, the type for our tag that we create right now. Yeah, and that means there is no tag. And instead, right at the end, we also push a byte here. And that will be the tag, which will be variant to num. Okay, let's call it maybe tag. Tag to variant. Yeah. Yeah, but tag versus variant is another thing. Really, like, it gets confusing otherwise, you know? Oh, that would be cool. Making like a whole refactoring through the entire compiler where I'm just making these names consistent. Okay, so the tag will be waffle byte of the layout dot variant to tag of our symbol. So tag dot symbol. There are no definition. Oh yeah, dot get. Hell yeah. So a switch means we get the type of the enum. Yeah, we have cases, which will just be layout dot tag to variant, I guess. Tag to variant dot size, I think. And then here we can say layout dot tag to variant means we get the tag and convert that to this. Okay, yeah, and we also need to be able to convert a yogurt body to waffle, which will basically need the same things as this one, I think. So, you know, Yeah, this will need the fun and other parts. Fun and yogurt ID to waffle expression. Okay, this doesn't work. Interesting. Oh yeah. Cases.set. Oh, probably it's a mutable thing. No, T is empty. Well, what about this one? And what? Oh, it's a slice of waffle bodies. Oh yeah, because this does return a waffle body. Sure. Waffle member of int. Waffle member of some expression, right? So the switch condition. Yeah, switch condition. We need to get that thing. That waffle expression. So this would be switch.condition, that's a yogurt ID, and then we say yogurt ID to waffle expression dot get switch condition dot waffle member. Yes, so from the condition we get the tag, which will be 1 byte. Perfect. Oh yes, this will be memory layout params. Alright, so params layout needs a size and an alignment. Sure. I'm just thinking if we have multiple multiple builders basically. Yeah, I'm afraid that an inner body, for example, can also add IDs here, so it should be able to mutate this map. So this will actually have to be a mutable map, and similar here. Because basically we're just taking this part, and like this is basically what we want when building a body. Where we take the function builder and its body. Yeah. And then for each expression in the body, we define a local variable. Yeah, I'm afraid we need to pass the fun builder around as well. Yeah, that is really unfortunate. Hang on. Fun builder. Returns a waffle fun builder, which just has locals. Oh yeah, and I see. Here we need to be able to add locals on the waffle body builder as well. Yeah, okay. Okay. Yeah, I guess. So, yeah, and here we also need to pass around the Waffle fun builder. Takes a fun builder, I guess, which will be Waffle fun builder. Beautiful, kind of. And same here. So this will also need the fun builder. Sure. Oh yeah, this needs the fun and also the fun builder. Okay, so we push the body expressions. Okay, yeah, we get expressions for that. Put them into the map. And then in here, we just return yogurt ID to waffle expression.get of the body return expression. Yeah. And now in here, we can just say fun.body.toWaffle. And of course, that needs the fun, it needs the fun builder, and it needs yogurt ID to waffle expression. But it is more high level now. Oh yeah, and that doesn't exist because that was only created in here. But this should work. Nice. Very, very beautiful. Okay, yeah, I guess that's true. Let's see what to do next by just running this and seeing where we crash. So memory layouting parameters. Actually, the memory layouting, that's cool. Yeah, this efficient layouting down here. I'm just going to, I think, copy that somewhere up. I'm not actually sure what to do. Okay, structs, enums, yeah, that's like very... Okay, this down here. This efficient layouting is not quite... That's basically the foundation of all aggregate types, where we may want to reorder things. So, layout efficiently, where we have some parts which will just be memory layouts, aka something with size and alignment. get this struct and move that up here as well. Layout efficiently, and then we have some parts, and it's gonna return, I don't know, parts layout, I guess. That has a size and an alignment, and then, oh yeah, it's gonna have parts. Yeah. Ooh, that's cool. Aggregate layout. Layout aggregate of parts returns an aggregate layout. Nice. This basically tells you that it has some aggregate parts, and yeah, aggregate part is either some padding, so there's an enum, or it's like a field. I'm not sure how to call these, to be honest. Parts is a nice word for that, but also these don't contain padding. I want these to be parts. Like parts are always, you know, basically the fields of an aggregate, or like the, you know, the things that are next to each other in memory. And these parts can be padding, or they can be some input or field, or yeah, let's call them fields maybe, or some fields, or some field with an index. Yeah, and then here we have that field to offset. Yes. That's it. Nice. That is super nice. And this is not actually, like, this to do belongs inside of this function. This is only, you know, we can just make the implementation of this function more efficient without changing the API. Okay. Okay. Oh man. So these are not parts, but these are fields. Yeah, and I mean, for now, let's just continue doing something very, very simple and stupid. So let's maybe rename input to, I don't know, field, I guess. It's going to return an aggregate layout that has parts. So yeah, field to offset will be a map. Just because that's more, you know, a slice, yeah, I suppose like a slice is more efficient than a map. Yeah, but I'm going for clarity here, so that when I read this code later on, I'm not like, what the fuck is going on here? Yeah, field sorted by offset doesn't exist, but instead we have parts. And these are interesting because these are really like aggregate parts. Okay, so we have parts and we have the fields to offset. Yeah, let's also have the size maybe, and the alignment. Amazing. Like these are the things that are in the final, struct. But also these are the things that we build up while we're iterating over the fields. Okay, so we're iterating over the fields. Like, okay, we have this layout. And let's maybe first say, hey, let's add some padding. Hang on, I had something like this somewhere. Well, size before padding is size. And then we say size equals round up to multiple of let's get the index separately, I think. Let's just call this field. Multiple of the field alignment, yes. And then, if size before padding is not the same as the size, then we also add padding as a part. So parts dot push aggregate part dot padding of the difference, basically. So of size minus size before padding. Yeah. Then we have aligned the aggregate, and then field to offset push size, beautiful. And then, yeah, this doesn't really exist, but instead we just do parts dot push aggregate part dot field of the index. Nice. And then we say size equals size plus field dot size. That's basically that. Yeah, and the alignment is the maximum alignment of the field alignment. Ooh, yes. This is going to be put of the field index. And yeah, size is just size, alignment is just alignment, field to offset is, yeah, okay, field to offset dot slice. This doesn't work because this is a map, sure. And then we have the parts. Yeah, the parts are converted to slices though. Like this. Nice. So we can build aggregate layouts, and we don't reorder the fields and add padding where needed to reach the alignment. Layout aggregate. And that's like the foundation of all other layouting things. The foundation of most other layouting things. So for example, laying out function parameters, where we basically have the params and return the params layout. Okay, yeah, and I think here we just lay out those types, I guess. Layouts. It's going to be a list of memory layouts. And for each param, we memory layout that. Yeah, param.memory layout. That returns a memory layout, and then we add that to the layouts, like this. And then we say layouts dot to slice layout aggregate, that returns an aggregate layout. Yeah. Layout. And then we return a params layout where the size is, we just copy the size and alignment. Nice. So let's see where this fails now. Ooh. Oh yeah, memory layouting, an arbitrary type. That's what happens down here. So let's look at that. Layouting a type. If this is a primitive type, yeah, like an int. Yeah, okay, if it's an int, then we just do, this without that. We just do this. This is memory layout. Okay, so let's align this. Look at how obviously parallel this is. Clean. Yeah, if it's never, then we don't, like, this has no memory basically. Okay, if this is a struct. Oh yeah, now we basically need to memory layout struct. We need to call that. And this is actually what I'm gonna, this is not something I'm gonna do. I'm just going to copy this code up here and, well, ignore the result. And maybe comment this out even. Yeah, let's comment this out. Yeah, sure. Was it memory layout struct? Memory layout struct of the type, and that's going to give us a struct layout. Okay, so that should also have a size and alignment. And we could calculate those on demand based on the parts, I guess. Maybe. No, let's not do that. Okay, so yeah, layout this. This is gonna return a layout, and then yeah, we do this. Exactly this. Amazing. Then for enums, we will do something very similar. We'll just move that up here. Yeah. Sweep that under the rug. Like, we don't care about that yet. And in here, just get the layout. Like type dot. Yeah, that's better. Memory layout enum. Let's do the same thing here. And do memory layout. Ooh, no. Let's just do layout size and layout alignment. Okay. And for a lambda, sure, we can do something here. Let's just do to do for now. And yeah. Look at how concise this is. It's really nice. I think this is recursive, belongs more to the enum case actually. So let's maybe put that here. And maybe this, yeah, I'm gonna put this up here. Yeah, I like that. Cool. Yeah, size and alignment are not a thing for enum layouts, and that's a shame. Let's do that. Size and alignment. Very cool. Yeah, what fails now? Memory, because we create an enum, that actually makes sense. I want to get structs working first, I think, because they are a bit simpler to work with. So let's actually just do, I don't know, foo equals end, where x is a and y is 42. And then we return foo.y. Okay, so struct literals have to be multi-line for now. I think that's the error. Well. Oh yes. Okay, so we create a comp time 42, and we don't know how to do that yet. Yeah, let's do that. Converting a yogurt value to a waffle expression. I think we'll just switch on the value. Yeah, the value is one of these. Yeah. So if it's an int, a comp time int, then we just build a waffle word of that int. If it's a comp time known string, then we create a waffle struct, which is more like an aggregate, with two things inside. There is the pointer and the length of the string. So this will just be string.data and string.len. But these have to be waffle expressions. So this will actually be a waffle word, and this will be a waffle word. Like this. Okay, for a struct with some fields, well, to do. For a tag, to do, lambda to do, plum type to do. Okay, yeah, YogurtValue dot kind. Yeah, waffle word of an address. No. So data to int, I think we can do that. Sure. Look at that. Memory layout struct. Yeah. Let's do that. Structs. Kind of not difficult, but we need to make sure that the memory layouting is always deterministic for equivalent plum types. So we may have, for example, a plum type struct with fields x and y, and another plum type struct with field y and x. And those are compatible, and they should have the same memory layout. So when memory layouting these, I think the first order of business would be to put the fields into a deterministic order. If there are we do the aggregate thing up here, like layouting the fields in this aggregate. We want some aggregate of the fields, and one way to do that is to reorder fields and do everything efficiently. But for example, for a point where x and y are both just ints, like reordering doesn't make a difference. So there is no natural better way to order one. And ordering x and then y is just as memory efficient, just as valid as ordering y and x. So for these cases, even though we may reorder fields up here, we should still respect the order of the field. I'm going to document that here. Now, if there are multiple valid. I don't even know how to put that into words. Maybe it should be deterministic. Yes. Is deterministic. Now. Okay, so let's just grab the fields, which are a map from name to value. And I think we can just, take the fields, maybe order fields by name, like layout fields is the first thing we want to do. Or do we? Okay, order fields by name so that the memory layout is deterministic. Even if multiple definitions of the struct use different orderings. Beautiful. And then what we do is something like this, probably. I'm not going to call it fields, but just like field names, maybe. So field names. And for each field in fields, now we do field names dot push the key. And I think there's a sort function in the standard library, so field names dot sort. Damn it. Oh, does it take a slice maybe? Yeah. Martinez doesn't have closures, so with these higher level functions I'm always a bit cautious or anxious that things won't work, like they will be very verbose. But apparently we have sorting, so that's at least something. Yeah, next lay out the fields, and that's basically what we do down here already. Yeah. Lay out the fields. Field layouts is a list of memory layouts, correct? And then field, for each field in the, hang on. No, the order will be the field names. So for each name in field names, field layouts to push the field with that name memory layouted. Perfect. And then let's just say field layouts is field layouts converted to a slice, so it's immutable. Okay, yeah, and then we want to lay out the aggregate using this layout aggregate function of this slice of memory layouts to get an aggregate layout, which then has a size, alignment, and all that nice stuff. Lay out the fields efficiently. So this will just be field layouts and layout aggregate. Nice. That gives us an aggregate layout. Now let's just try to build, like a struct layout and see how we map things. So the size will be the layout size. The alignment will be the layout alignment. That's the obvious part. And then the next question is what else? Like we need parts, which will be a slice of struct parts. Okay. Let's just do that for now. And then field to offset. Map string to int, yeah. Field to offset. Okay. Sure. Yeah, and all this is basically no, not exactly. Like this is kind of the parts thing. This is the field to offset thing we had. Yeah, I think let's just go over the parts. Like for part in layout at parts, do, and then we basically just do parts.push, and we switch on the original part. If that's padding of some amount, then we do, we push struct part.padding of that same amount. And yeah, if that's a field of an index, then we just push a struct part field of, field names dot get index, like this. Beautiful. Yeah. Size, alignment, parts, field to offset. Nice. Yeah, and field to offset, basically for, what does the aggregate thing have? It has field to offset, but it's into it. So for entry in layout dot field to offset, we do field to offset dot put entry dot key, but that's an index. So we do field names dot get of that, and we map that to the actual offset. Okay, and then we return that. That is amazing. Yeah, map aggregate layout to struct layout. That is pretty cool. That is actually cool. Okay. Ooh, this is, Okay, so the function parameter has some ID, and we need to make sure, like, we don't know where the parameter is. We don't have a Waffle expression for that. So I think we may need to add that to the, how do Waffle functions, like how do parameters work there? function just has local variables. Oh yeah, they don't explicitly contain parameters. Instead, the local 0 just represents all parameters. Oh, that's interesting. Okay. Sure, we can do that. So we basically want to we have some parameters, we lay out them, and then we add that as a local variable. Waffle fun builder. Oh yeah, they are probably already added as a local variable. Oh yeah, but local ID to waffle expression. Here we need to put the parameters in here. So I think we'll need fun dot for param in fun dot body params do yogurt ID to waffle expression dot put, and now we basically want to map the parameter to its offset in this param layout. So param layout dot I don't know, param to offset or something like that, dot get the param, which is gonna give us the offset. And oh yeah, the corresponding waffle expression will then basically be, hang on, waffle local, I think. That needs a waffle ID, which will be the index, so waffle ID, where the index is 0, the parameters. And then the size and alignment. Probably. Yeah. Size will just be I guess param layout. Oh yeah, param layout dot. Oh, okay. So we have this local variable parameter. Now memory params. Yeah, let's maybe map this, like save this. Okay. Param aggregate is this. Kind of intermingle with this, I think, because not at least semantically, we create this and then waffle local is okay. So param aggregate is that. Yeah, and then yogurt ID to waffle expression is nothing, and then for each parameter in the fun body params, yeah, we basically put in here mapping from that ID to the param aggregate. Dot, oh I see, param aggregate dot member or waffle member. At that offset. With some size, so this will be param. Param. Yeah, I don't know. What size and alignment. Oh yeah, I think this is better. This is much better. So we say we have our layout, which will just be fun.getParam.type.memory layout, whatever type that is, you know. And then we put the aggregate.waffle member with the param offset, and then layout.size and layout alignment. Yeah, like that. Beautiful. Next. Waffle member, comma. Well, no, that doesn't seem right. Oh no, what did I do? Yeah. Hopefully this is correct. I think I like accidentally had multiple cursors at some point. That sucks. So here we get the struct layout, the field layout, and then we just return a waffle member. Of that. Which means we can also do this. Hell yeah. Yeah. It's all like, we don't want to depend on this iteration order to be the same as up here, so let's just rewrite this into something a bit more clean. So first we just get the params. We just get the IDs in some order. So this will just be that. And fun.body.params do params.push param. Okay, just getting the IDs of the parameters. Nice. Then getting their types. This will be a list of plum types. And then for each parameter, we do param types dot push type. Okay, that's it. I think I'm gonna move some of this into the memory layouting, so that the memory layouting just deals with the yogurt IDs for parameters. You know, similar to how here we have like parts and fields and so on. In here we just have, hang on, but it's the index. Yeah, they are referred to by index. And when we have parts, which we need when constructing params, for example, when calling a function. For now, let's just leave that out. And then we have param to offset, which will be a map from int to int. Okay, that's fair. Cool. Okay, yeah. So then in here we do this. Okay, you know what? Sure, let's do memory layouting directly. And then let's do memory layouting. Okay, we build a builder with a param layout as the local thing. And then let's do yogurt ID to waffle expression. Yeah, which will be a map. We go over the parameters. We say, you know, the layout of this parameter will be the layout of the type, I'm sure. And then in here we'll just put param to param aggregate, the waffle member, param layout, param to offset, get param, and then the layout constraints. Okay, yeah, that seems correct to me. Right, so in the memory layout, in here for the params layout, we need to find the offsets. So I think let's just do param to offset is a map from int to int, and then for each, you know, parameter in params, hang on, map from int to int, we already have that for the aggregate thing. Field to offset, that is amazing. So actually, param to offset is just field to offset, and that's it. No copying needed. Oh yeah, layout dot, like the aggregate layout, field to offset. Oh, look at that. Okay, get some yogurt ID. That does not seem correct. Right, so here we have the parameters, and I think we want to enumerate them to ensure that we have the same iteration order. And this is like the actual item, and down here we just take the index. That works. Like, we can do this. Okay, compiles. That's nice. And we have, whoa, we have a waffle. Damn. Okay, let's see. So each expression got mapped to a waffle expression. Oh yeah, this is just, it's all indented, but just by zooming in. It wraps around. Okay, so we have expression number 1, which is a word 42, size 8, alignment 8. There's this one right here. Then we have this, which is a struct. So 2 is some struct with size 16, alignment 8. Beautiful. And it contains 2 fields. Field number 0, which will be the parameter of this main function, which is an int, which is size 8, alignment 8. And this function could have multiple arguments, so we also say .member 0 with size 8, alignment 8. Nice. That is pretty nice. And then we do something. There's also 1 in here, and that's a reference to the one we defined here with alignment size 8, alignment 8. Beautiful. What? And then down here we say let's access the struct.y. That is this right here. We take the 2, which is size 16, alignment 8, and we say .member 8. To get the thing at offset 8. So this has size 8, and at offset 8 there was this. So then we get something with size 8, alignment 8, and that's basically the y from the struct. And then we return that. Damn. That is pretty amazing. That is... Whoa. Whoa. Yeah. Cool. I like that. Yeah. I'm probably gonna continue working on this tomorrow, because there are still a few to-dos in here, and I don't really have time today. So there are, let's see, okay, to-dos for the literal comp time values. That's fair, I think. Then for more complicated expressions, like creating lambdas and so on, okay, that's gonna be a bit more tricky. Built-in instructions. True. And then, oh yeah, that's it. Oh, and memory layouting of enums probably. Yeah, exactly. And of lambdas. Sure. Yeah, we'll do that next time. And so I guess see you then. I'm back. So I guess let's just continue with yogurt values. Yeah. How they're constructed depends on the memory layout of the type. So I think we actually need to get the type. And for example, for structs, we can get the, what's the memory layout? Struct. And then iterate over the parts. So for each part in the layout parts, we basically just switch on the part. Yeah. And well, it can be a field, in which case we're just gonna convert the field value to a waffle expression, I think. Oh yeah. Okay, so this would be fields.getName, that's the field value, converting that to a waffle expression. And basically we want to build these build parts and put them into an aggregate thing. So basically create this list of waffle expressions, and then in the end we want to return a waffle expression waffle struct, yeah, of these parts. Yeah. If we have a padding, then we want to add something else to the parts, namely waffle padding of that amount. And let's also like wrap this in parts.push. Okay. This looks fine to me. A tag is basically an enum. So this is actually a tuple of the tag symbol and the payload, or the arguments. So I think we should do memory layout enum to get an enum layout. And it's actually very similar, so yeah, let me just copy that. In the end we return a waffle struct, more like an aggregate. I should change the name of the parts. And yeah, the enum layout has a particular layout for every payload, like for each variant. So I think we can get, was it variant layouts or something? And get the variant for our part. Yeah, there's no variant layouts, but there should be something similar. Payload parts. Oh yeah, okay, so these are only the parts for the payload, which can be fields or arguments with an index, in which case we just want to get the corresponding argument. Yeah, okay. Something like this. And yeah, I guess that's it. Yeah, I'm gonna leave these as to-dos for now. Oh yeah, we also need to add the tag itself. So how is that represented? Tag offset, I mean, yes, sure. Oh yeah, this is the interesting one, variant to tag. So I think we can just do parts.push tag, hang on, waffle byte of, what's a variant to tag? Yeah, getting our tag from that. Okay, nice. Yeah, that should be it for values. I can zoom out a bit. Yeah, this looks fine. Oh, let me actually create an enum. I think that makes sense. So that would be the test.plum file. Here, creating a struct, creating an enum. Yeah, let's say this is actually like sum 42. Create maybe of 42. Calling this. Yeah, let's do that. That should be a comp time value. So, all right. Yeah, I guess. Interesting error, actually. Would have guessed that. Oh no, yeah, it's fine to return. I see. Yeah, okay. Let's do it like this. I assumed this was like a switch, and these should have incompatible cases, but I mean, yeah, it's totally fine to create a struct containing an int and maybe int. Okay, so there's a to do in memory layout enum. Oh, I thought we already did that. Oh, no, we don't. Okay, sure. So how does that, what should that do? Oh man, basically, we have a type. We know the type is an enum, so let's do something similar to this, but with variants. So now this is an enum type. Actually, I think this makes sense. Looks something like this. I'm just going to copy this and then kind of merge these, I guess. Okay, so basically this part right here has a size and alignment. I mean, sure. Then we have the payloads, yeah, the argument offsets inside of them. We have the tag offset for int. I think we had an enum, what was it, payload offset or something. I'm going to reintroduce that. Well, and payload layout, which is basically going to have this, the parts and the offsets. And then in here we just have payloads, and this is a map from string to payload layout. Yeah. We could also do this in there. I think that makes sense. Just put byte in here. We don't have this map. Yeah, I like that. Yeah, and I think like this should be yeah, well, I need to decide on this, so yeah, maybe let's put like a readme and put some to-dos in the readme. Enum args versus enum payloads. But there's also other to-dos. Oh yeah, Waffle struct versus aggregate, because they don't really have to do anything. Have anything to do with normal structs. They don't. You know, this aggregate things. They don't have the fields in them. They don't have names. They're just integers. And yeah, and they can have padding. So that's kind of weird. Okay. Yeah, we have arguments versus payloads, waffle struct versus aggregate. Yeah, I think that they're the ones that I want to keep track of. Okay, so mapping these. I guess first of all, like, having multiple enums, like an enum that is true or false should be the same as an enum that is true or false. That is false or true. Yeah. So which tag we assign to which variant should be deterministic. And I think that should just be alphabetic, actually. So let's do that first. Order variants so that the tags, enum in subsection for enum. Yeah, tags versus byte versus symbol. Yeah. Order variants by name so that the tags are chosen deterministically, even if multiple definitions of the enum use different orderings. Okay. So we have variant names, just a list of strings, and then for each variant we push the key. Totally fine. Yeah, I think then we can, I mean, we already have this map, kind of, you know, because this list or slice of strings is very similar to this map. Like you have an int, or like a byte as an index, and you get back a string. You can do the same thing here. Yeah, let's move that. Let's convert that to a slice, by the way. Like, yeah, okay. Anyways, also, is that not needed? Probably not. Okay, so laying out the fields. Yeah, no, we don't do that. We do something like this per enum variant. You know, yeah, basically building a payload layout for that. I'm just gonna move that in here. Yeah. So lay out the arguments. Yeah. Instead of fields, these are called arguments. Yeah, something like this. Oh yeah, we don't have arg names, and we don't need them because arguments are ordered anyways. So yeah, for everything that is like indexed by name, we need to sort them and then like, do complicated things, you know, to make the layouting deterministic. For arguments, they already have an order, so we can just take the variant value, which will be a slice of types. Yeah, name is weird. That's actually like the argument, I guess. And we can just directly memory layout that argument. Makes sense. Okay, and then we have this slice. Okay. Cool. Yeah. And then we map the aggregate layouts, the aggregate layout that we get to a payload layout for this one enum payload. Very nice. I guess, you know, let's maybe take the part, or the parts will be payload parts. Does that exist? Enum part exists. Now let's rename that to payload part, I think. Okay, and then for each part we basically push the part in here, poor man's map basically. Yeah, arg doesn't exist apparently, but instead what we do is, oh, field. Interesting. Yeah, field with an index would just take the payload arg of that index. Nice. Yeah, and then we need this offsets. Oh, I see what went wrong there. During the renaming from field to arg, we also renamed the fields, which are semantically different, from the aggregate layout. I see. So yeah, this offsets thing will just be a list of ints, I guess. Then for every entry, yeah, not this. We do, I mean, yeah, let's turn this into a slice, I guess, of some length, basically for each field, each payload, I don't know. Yeah, and then in here we can just set one of those. Yeah, the entry key will be the index, and the offset will be the entry value. Okay. And then in here we have a payload layout. And in here we can do payloads being basically this, you know, a map from string to payload layout. And then we can add the newly created payload down here. Put, I think. Okay, yeah. Yeah, arg to offset doesn't exist, that's just offset, I guess. Yeah, offsets. Oh yeah, tag is missing. Oh, that would be the index of that thing in here. Oh, that's pain. Yeah, let me maybe create, you know, a reverse map or something. Name to, what is it? Name to tag, I guess. Something like this. Yeah, basically for each variant names, but also, you know, in an enumerated way. We basically just put something in the map. The item, which will be the string, and the index, which will be a number converted to a byte. So I think there's a lower byte function. Yeah. Okay, beautiful. Then the tag is missing. Well, true. So tag is variant to tag and getting the variant key. And they don't really have a layout, or like a size and alignment, you know. Yeah, variant to tag is not in scope. What was it called? Name to tag. Oh, that's, yeah, no. Yeah. Variant to tag. Okay. Yeah, then we have payload layouts. Basically this part right here. Next, tag offset and tag to variant. Tag to variant is basically a version of this list right here. Let's maybe create that. Tag to variant. Like, it's basically the reverse part of this, which is interesting. So yeah, this maps bytes to strings, and then we do basically this the other way around. Oh yeah. Cool. Cool. We do need to get the size though. That is kind of difficult. So I guess we can say, you know, we have a size and alignment, like initial ones, and then when layouting these, when layouting these we also have we update them, you know, basically while going over the enum variants. We layout them, we map them to the payload. Yeah, I can do that before here, I think. Yeah, size is the maximum of the size currently, and the layout and the size of this payload layout. And similarly, yes, basically the same for the alignment. Like update the global payload size and alignment, something like this. Yeah, maybe I should rename them to payload size, payload alignment, because these don't contain the tag. Okay. Yeah, something like this. But now the difficult part is that we also should update these. Like, you know, we should basically add a padding part at the end if this payload is not big enough, basically. But that's tricky because, you know, we build these payload parts for each layout individually, and I think, yeah, we basically need to make a second pass on these parts and add padding afterwards. Yeah, and this is a slice which is not mutable. Oh man, so let's maybe, yeah, instead of having the payloads directly here, let's only have like separate parts and offsets maps, I think. Like this. Kind of sucks, but I guess that's it. Yeah, and this would be a slice of int. Like that doesn't need to change. And this one's not a slice, but a list of payload parts. Okay. Yeah, and then down here, instead of doing this and this, we just save the individual parts, like payload, what was it, parts, put variant key, parts to slice, and payload offsets, put variant.key, offsets. Why doesn't this work? Oh, yeah, because we don't convert this to a slice, so we can mutate that afterwards. Cool. Yeah, so we've basically mapped the aggregate layouts to payload layouts, information for payload layouts, I guess. Oh man, yeah. Hang on. Yeah, we could just save the, what was it? The aggregate layout directly. Let's actually do that. Yeah, let's just have a payload layouts. And it just has an aggregate layout like this. And then we don't do that in here, but instead we just say payload layouts. Put variant key layout. So first we lay out all of the variants, and only then we basically build the variant the payload layouts. Yeah, this will be a map from string to payload layout. Yeah, that's confusing me. Payload layouted payloads. I don't know. Yes, I don't know. Something like this. Okay. So, yeah, we build up the parts, being payload parts. Sure. And yeah, then we just get the payload. That would be, let's call it like payload aggregates. I think that's fine. Yeah, this is payload aggregates.get variant key. Yeah, then we have these parts, and then basically we can add more padding. You know, map parts. That's basically what we're doing. Add padding at the end, so that all payloads have the same size. That's important. And the way we do that, I think, is just by, oh, what's going on here? Payload aggregates. Sure. We basically look at the layout size and see if that's different from the payload size. Yeah. Like size diff needed padding. I don't know. Is, you know, the overall payload size minus the actual size of this particular enum payload. Should we name this even further, like max payload size? I think so. Like that's explicit, you know. Max payload size is maximum of max payload size and layout size. And then here we just take the maximum payload size minus the size of this particular layout, giving us the amount of padding that we need when we store this variant. And then we can basically check if needed padding is not 0, then we push another part. So parts.push payload part tagging and of the needed padding. Okay, amazing. Cool, then yeah, map offsets, I guess, sure. And then construct payload layout. And that would just be payloads dot put variant dot key payload layout. It's not called that way. It is. Yeah, that contains parts, which we have. It contains offsets, which we have, and contains a tag. Yeah, parts are basically our parts. Offsets are our offsets, and the tag is variant to tag of our variant. Beautiful. Whew. Okay. Then we can actually build the entire enum layout, which needs a size and alignment. Payloads, which we have the tag offset and tag to variant. Yeah, let's just build that. You know, let me copy that down here. Okay, so the size will just be the max payload size plus 1 for the tag. Yeah, the alignment will be the max payload alignment. The payloads, we have them. The tag offset will be at the max payload size because the enum tag will be after the payload. And tag to variant already exists, doesn't it? Yeah. Amazing. And that's it. That's it. Beautiful. Payload parts is not a field. Okay, 373. Why don't I get an error for that? What's that in Waffle? Oh, I probably do get an error, but only if I have this file open. Yeah, payloads get. Oh yeah, no, I think we can just do payload layout, or like a variant layout, I guess, which will be layout.payloads.get tag.a, and then in here we can say variant layout.parts. Beautiful. Yeah, and then we also need to get the variant payload.tag. Hang on, we never need the original layout, do we? Nope. So let's just get the payloads directly. And that makes sense, you know, because we are only interested in the layout of this variant actually. Yeah, let's call this variants, and this will be a variant layout, and this will be variant part. Yeah, and let's just have the tag as byte in here, because why not? I think that's a bit more clean. You know, this basically tells you how to construct the variant. But then again, we basically support two different use cases here, you know. And constructing an enum where we need the parts, and then inspecting an enum where we need the offsets. Maybe it does make sense to... I'm gonna leave it like this, and I'm thinking maybe it makes sense to put these actually into two separate maps, because one of these, you know, concerns itself with constructing an enum, and the other one with accessing an enum. That's fine. Okay, so this will not be a variant. Oh, yeah, it will be a variant layout, but yeah, this will, let's not call this payloads, but variants. Oh, oh, variant layouts, I guess. Sure. Yeah, and then in here we have variants, but this is like guaranteed to clash with other names. You know, when you use the enum layout, okay, that's probably fine. Yeah, let's just say variance is that, and then in here try to initialize field tag, but it doesn't have that. That is, where's the field? What? I don't get it. We don't get it. Try to initialize field tag, but the variant layout doesn't have that. But what? Where do we do anything with a field? I mean, we do have the tag, which no longer exists. Oh, try to initialize. Oh, I read this as the tag that is called field. You know, try to initialize the field tag, but actually it's supposed to be read the other way. Try to initialize the field called tag. Oh, oh man. Yeah, I think, you know, for cases like these, you should really put quotes around custom names. I was like, oh, what's going on? Okay, yeah, that makes sense. That makes sense. Okay, so this should not go in here, but instead we should put, like, push another part. Yeah, add tag, which will just be parts.push a variant part.tag byte tag. Yeah, tag, which is a byte. Sure. Just like this. Hell yeah. Yeah, in the Waffle, sure, we are using this incorrectly. That's to be expected. So yeah, we can get the variant specific layout, and then for each part, we basically switch on the part, and this can also be a tag with a byte, and then we turn that into a waffle, a byte of that byte. So we don't need this as a separate thing. Okay, amazing. Yeah, what's going on down here? Oh, and creating a tag with a runtime known thing, like we get memory layout enum. Okay, this should be pretty similar to what we do up here, actually, shouldn't it? Just getting all the parts and stuff like that. I think so. Yeah, let's maybe copy this and then see what we can do. So this will be the expression type, memory layout enum. We get the corresponding variant, which in this case is called symbol because this is a proper type and not a tuple. Totally inconsistent, I know. We build parts, and then we push thingies, and then we create a waffle struct of the parts. Okay, so far so good. Yeah, this is like all the common part. We only need to unify these for loops, basically. In this case, the padding is the same. The argument looks a lot better down here. Yeah, tag, we have that as well. We have a waffle byte here, that makes sense. Okay, so it should be like this, right? Okay, that's some other to do, I think. Amazing. Okay, there's a to do in toWaffle. toWaffle of yogurt expression. toWaffle of yogurt expression, and indeed there are some to do's down here. Question is, what to do is it? Yeah, I know, inefficient, but okay, implement calls is what we want to do. That makes sense because calls, like, really they should work. Yeah, calling is something that depends on how do we call something. I think in the waffle there's a call expression. Let me see. Yeah, there's a waffle call, which has a function, waffle signature, and has arguments, which is a single waffle expression, which is probably an aggregate, which you know, contains an aggregate that contains all of the different arguments layouted in an efficient way. Okay, so let's look at how the parameters of functions are laid out, because we already do that. And yeah, calling functions basically need to have the same memory layout. So when we convert a function to waffle, we push the parameters to some yogurt ID list. Sure. And then we push the types. And then we do memory layout params. That gives us a param layout. And yeah, so basically a function assumes that parameters come in this memory layout, in this shape. And that means that some of the parameters may be reorganized, like reordered. Let's say you have a function that accepts a byte, an int, and another byte. Then actually, like on the stack, they may be in a different order. You may have the int and then the 2 bytes, for example, because that saves memory. And the exact memory layout that functions expect is also the memory layout that we need to respect or construct when we want to call a function. So I'm just going to copy this code to here where we compile the call. Okay, so from the point of view of this call side, these are not called params but arguments. And yeah, what do? Well, we just get the argument types, which I think makes sense. And then for all of the arguments in this call, we push some type there. Okay, makes sense. We memory layout them. That is nice. And now we want to, well, basically actually put them, like, create an aggregate that contains all of the arguments. So that will be somewhat similar, I guess, to what we did for structs and enums and so on, where we just, we have memory layouted them. Now we want to do something like this. Create some parts and create a waffle struct in the end that will contain the parts. But actually, hang on. This will be arguments, and then we will return a waffle call of some function that has a waffle signature. How are signatures mapped again? I think it's just like literally taking the string from the function. Yeah. Okay, so yogurt fun probably has, like, yogurt call knows the function that's called, that's a yogurt signature, and we'll just map that to a waffle signature very naively by copying the string. That should be fine. So creating a waffle signature where the string is the call, what was it, function? Receiver. Ooh, interesting. I want to rename that at some point, so let me add call receiver versus function. Yeah. Okay, and we need the arguments, which will just be this. I think. Nice. Yeah, a waffle struct of, or basically a struct containing all of the arguments laid out in the same layout, because this is deterministic as the function expects it. Okay, yeah, so we go over the parts. Param's layout doesn't have parts. Of course not. That would be too simple. Oh, it just has, basically has all the information you need for accessing parameters, but not for putting them in place. So I think we'll need parts, which will be a slice of param part, I guess, or param's part, technically. A param. Struct part is what it's called down here. Param's part, yeah, param's part. And yeah, basically the argument might be some argument with an index or some padding. Sure. So we lay out the aggregate, and now we need to map the parts. So first construct the list params part, and then basically for each part in the layout, what was it, layout parts, we push something here. Yeah, so just padding of some amount resulting in params part, or padding. And this field, which results in params part.arg of that field. That should exist, yeah. Okay, and down here we only need to also take the parts, which will be parsed, converted to a slice. Okay. Yeah, so this can either be padding or it can be an argument with an index, and in that case we just get the corresponding argument from the call arguments and get the corresponding waffle expression for that. Yeah, so this doesn't work. That sucks. Oh, arguments of waffle call expects the size and alignment. I'm not sure. Is that the size and alignment of the return value, basically? Or like the return type, or is it the size? Does it include the size and alignment of the arguments? I think it's yeah, it must be of the return value. So I think we document that here. The size and alignment are of the returned value, not the arguments. Beautiful. Yeah, that also means that we need to look at the return value of that function, right? So basically, looking up a function, I guess, which means we need more information up here. Yeah. I think we need the yogurt. I need the yogurt. So this will be yogurt.funds.get call receiver. Yeah, getting that function, then getting the return value of that, like return type, and then memory layer of that. Yeah, and then in here we can do, return layout size and return layout alignment. Okay. This call doesn't work, okay. Oh yeah, because we need to pass in the yogurt. Which means that this also needs yogurt. Which means that down here we also need to pass in the yogurt. Passing things all over the place, but that's fine. Yeah, value dot. Yeah, this also needs the yogurt. It doesn't just need a single function, but it, because it calls other functions and needs to know their memory layouts, their return types and their memory layouts. That means that compiling a function depends on the entirety of all other functions. Yeah, okay. So what's going on up here? Passing the yogurt and a lot of pieces. Oh, that's interesting. Oh yeah, the body has... Oh wait, I think there's like a return type. Yeah, there's a return type function for that. Nice. So what is what? Key yogurt ID 1 is not in the map. Okay. Sure. Let's see, we compile the yogurt to waffle. Okay, which means we get the main function and we convert that to waffle. Yeah, this function, which means we convert the body to waffle. That also makes sense, which means that we compile the switch. Hang on. Compile some expression. Not entirely sure what's going on here, but sure. In the end, something is not in a map. Why though? Key yogurt ID 1 is not in the map. Let's see where those are added. Like we have yogurt ID to waffle expression. Yeah, when iterating over the body, we add IDs there. That makes sense. Okay. When also initially the parameters are also in this mapping. Makes sense. We don't add bindings in switches. Like if you switch on some value in the yogurt, this yogurt switch will have bodies that take parameters, which are the payloads of the enum variants. We don't add those to the mapping yet. But you should still be able to, like we don't do that in our example code. So we don't have a single switch in here. Let's maybe simplify this. Let's say, let's just call create maybe, create maybe of 42 and then return 0, because why not? Okay, simple. So let's see, main int means we call, oh, I see. If we call some function and that function calls another function, that we don't see that in the call stack down here, because here we compile every function separately, because the API between these functions, the memory layouts, they are fixed, which means functions can be compiled basically independently. They just have to be able to look at other functions, but the order that they are compiled in doesn't matter, and they don't need to look into the body of functions. So let's add some logging here, like printf debugging, where we basically say waffling some function. Yeah, and the function does not have it does have a key. So then we know at least in which function the... Okay. So waffling cast from... Oh, right. We do have a switch in our code. We don't have an explicit switch. But we create an like a literal of the type sum int, like an enum with only one variant called sum that contains an int. We create that by writing sum42, and we convert that into this type, into an enum type, into a maybe, because the function claims it returns a maybe. So we need to convert that very specific enum type into this more general enum type. And to do that, we actually switch on the enum, and then we use the payload. Look at that, like YogurtID1. Yeah. Okay, so I guess it actually makes sense that we crash. Right, so we need to adjust how switches are compiled. For switch, yeah, we need to get the enum memory layout. That makes sense. Cases is uninitialized slice of that. Okay, sure. Oh yeah, down here we convert the case. No, we basically compile the case body. Yeah. And I think we need to add the parameters to this mapping of YogurtID to Waffle expression. So should we do that in this for loop? That's basically enough. We could also do them all up front. There's not really, like, both of these are fine, I think. Yeah, what are we iterating on? Take tag to variant. Yeah, I think, you know what, let's do that separately. For layout, like the variant layout, in layout dot variance, we do something. Yeah, layout variance was this map from variant, like your string, to the memory layouts of that enum variant. Yeah, that makes sense. Okay, so basically we need to map the parameters now. Let's just get the parameter yogurt IDs from the switch. So that would be switch dot cases dot get variant layout dot key. That is a body, I think. Like param IDs, the yogurt IDs. And that's a body, and the body has params. And then we can get the I'm not sure what to do then. Basically, for each of these IDs, we want to add something to the mapping, right? So basically, for ID in param yogurt IDs, which, oh, that's just in that, I guess. We do some stuff. What do we do? Well, we add them to the mapping. So yogurt ID to waffle expression dot put ID to a waffle expression. And I think that should be a waffle member of the original struct. How does that work down here? We switch on, oh yeah, on the condition. This basically. Let's factor that out into I don't know, this, I guess. like this is the condition waffle expression. Oh yeah, this is all like messy. Let's maybe like, put some new lines in here and make it all clean and yeah. Okay, so waffle member, yeah, condition.waffle member. But like this is the tag offset, that makes sense. Now we actually want to get some other members of that struct. So let's maybe 3 ints, like that's amazing. Oh, I guess offset, size, and alignment. Makes sense. Offset is, what is offset? I think we can get the offset from the layout. Yeah. I mean, we already have the layout for this particular variant, and that contains offsets. Look at that. Which is just a slice of int. So we can do offset dot. Oh yeah, we should enumerate them. Yeah. Yeah, and here we get the index of the parameter. Let's maybe do it like this. Yeah, we have the space. ID is param.item, and then we have the, that's fine. Yeah, something like this. Yes. Waffle member get doesn't work because this is a map. Why is that a map? Only layout key. Oh, that's map entry. Yeah, the item is the actual layout. Oh, map entries have key and value. Right. So we have a variant layout, and that layout has offsets. Okay. Yeah. And now we also need to get the size and alignment of that field. And that's not contained in the variant layout thingy. But to do that, we need to look in the we need to memory layout the actual parameters, I guess. So hang on, we have the ID. The param layout is fun get ID, get the type, memory layout that. And then here we can take the parameter layout size and alignment. Maybe it makes sense to not name this parameter because it's like a very generic term, but rather like binding or like, you know. I think that makes sense. Okay, so we have enums, and then each of these enum cases can, like, they have the bindings, which are the, you know, the payloads basically of the enum. Yeah, and then in here we just take the binding like the payloads. Yeah, payloads. Payloads is super nice. Okay, so we have payloads that are the parameters of this, and then for every payload we get the ID, and we lay out that. Sure. And then when you want to use that payload, you actually like access the original enum value. Yeah, and that will be the payload layout dot size and alignment. Okay. Cool. Damn. That's some complicated stuff. Whoa. Damn, this is a lot of stuff. Okay, so let's go the easy ones first. You know, casting an int to an int. We take the expression 0, which is the argument to this. Size 8, alignment 8. We get the member at offset 0. I mean, sure, that works. Create a maybe of an int. Means that 0, this right here, just contains the int. That's the argument to this function. Size 8, alignment 8, you know what you expect from an int. And then you say dot member 0, sure. That's basically the int. And then we create an aggregate containing that int and the byte 0. Okay. And the byte 0. Does that make sense? Because I think the maybe contains some or none, and they should be sorted alphabetically. M, N, O, P, Q, R, S. I think none should be 0, right? And 1 should be some. I'm not sure. I'm a bit suspicious about this one. Okay, but the entire enum aggregate thingy has size 9, alignment 8. Beautiful. And then we cast that. Oh, I see. Yeah, because this is not of the type maybe of int. This is of the type sum of int. And in here, the sum variant, which is the only enum variant, has the index 0. That makes sense. Yeah, okay. Okay. So now then we cast that. Sure. With this as the argument. 1. Just 1. Makes sense. And the result of that is another something, another value with size 9, alignment 8. And that's like the correctly mapped enum. And that's what we return. Amazing. Cool. So let's maybe look at other functions. Yeah, we have looked at these for now. Yeah, there's the main function, which is I think the next simpler one, and then the cast will be the more complicated one. Okay, so in the main function we create 42, sure. Then we call create maybe of int. The argument is this. It's the 1 expression, so it's just an int. Nice. And yeah, we put that in this aggregate containing only that, because that's the only argument, and the aggregate has the same size and alignment. And that entire call results in a maybe, which has size 9, alignment 8. Amazing. And then we create a 0 and return that. Whew. And now to the cast function. Okay. Yeah. At 0 is the argument of this type, size 9 alignment 8. Dot member 0 of size 9, sure, why not? And then we say dot member at offset 8, size 1 alignment 1. That is the tag of this enum. That is, the tag that we constructed down here. That's amazing. So we extract that byte from this aggregate thing, and then we switch on that. And we get, we do different things. Oh yeah, sure, for this type, there's only one case. It can only be 0. Amazing. Okay, and then we create this one expression, which is, well, calling cast from int to int. On something, on the original like sum of int thing, size 9 alignment 8. Member 0 with the same things, like that doesn't do anything. But then dot member 0 of size 8. So we basically cut off the tag at the end to get the payload. And that is the argument to this cast int to end function, which just directly returns that. So in the end we just have an integer. And then we create an instance of this enum, which will be this. An aggregate containing the integer that we just extracted from the other one, and then the byte 1 as the tag. Because in this enum, none has tag 0 and some has tag 1, because none comes alphabetically before some. That's crazy. Yeah, there's a size 9 alignment 8, and that's what we return. What? That is so cool. That is so cool. Yeah, I mean, obviously there are still to-dos in here, like lambdas and types and instructions and so on. Sure. Are there to-dos in the memory layouting? I don't. Maybe. Oh yeah, no, this should be like basically unreachable. And this, oh yeah, okay, sure. Memory layouting lambdas. That would be fun. Okay, yeah, but let me first commit this, because this is, I think, quite a stable state, basically. So, we did a lot of memory layouting and stuff. Yeah, we handled alignment. Yeah, reference counting is not like a concern of this compiler stage, but something we're gonna have to do somewhere else. Okay. Yeah, start converting Waffle to package. Not everything of that works, but the majority of things. Amazing. Cool. So what's next? Let's do some easy things like fixing terminology, because I think that makes things a bit more easy to wrap your head around. So in the Waffle, struct versus aggregate. I've been calling these aggregates for some time now, and I think that's the more reasonable term for this. So let's maybe Waffle expression kind. Yeah, that's not. Let's call this aggregate. Just some other expressions in memory next to each other. Nice. Yeah. And yeah, let's also name this to aggregate. And now there will probably be like lots of errors in here. But an aggregate has fields, right? Yeah, I think that still makes sense. Okay, yeah, does that compile? Not quite. So in here we still, oh yeah, indeed. We want to create aggregates instead of structs. Yeah, okay, that compiles. Let's also go through the mentions of struct to see if we really got everything. So creating and accessing a struct, yeah, just creates an aggregate under the hood. Yeah, sure. Badly aligned field and struct, yeah, that's totally fine. Oh, hang on, in aggregate. Yes. Then converting a yogurt value, yeah, that's semantically a struct. Memory layout struct, also fine. Yeah, struct expressions also exist. Yeah. Member has a struct layout. Instructions, sure. Okay, that's it. So if this compiles, then I'm happy. Okay. So, yeah, rename. Here's waffle.struct to aggregate. Okay, so we did that. And I also just want to improve the toString of the waffle, because this is like quite unreadable actually. Yeah. First of all, I think functions should basically tell you, what's the size and the line. Like, okay, one thing that makes this pretty unreadable is that we have size and alignment everywhere. So size and alignment, let's not do that. I'm just gonna comment this out. Like if we need to debug something, but we can easily add that back actually. So yeah, that's fine. Oh, dang, this is like actually readable. Dang. Okay, so there is some. Oh yeah, we want to know the size and alignment of the arguments of functions. So I think we should have to print them here. $0 as size, and then we just have I don't know, fun dot oh, I'm not sure. Well, let's just add this hint so we don't forget that. Okay, yeah, 0 contains args. And then we do this. Yeah, this doesn't tell us anything. Like, the interesting part here is the size. Alignment, I'm pretty sure that's gonna work out. But the size is something crucial we need to know for members. Yeah. Member 0. Member.size. Hope the member doesn't contain the size. Right, because the expression contains the size directly. Makes sense. Yes. Oh yes, member 0 size 9 and member at offset 8 size 1. Nice. I am wondering though, why do we even... Oh, I know why we do this. Because we have this aggregate of all arguments, and then we get this specific argument, but there's only one argument, so this basically means nothing. I think we can actually be a bit more lenient, in how we create Waffle, because I think we need an optimization pass on waffles. Basically, like a compiler stage that takes a waffle and creates another more optimized waffle. For example, instead of having this in here, we could just put that 42 word directly in here. So then when you're compiling this to bytecode, we don't actually put this on the stack somewhere, and then here we say, hey, copy this from the stack, but instead we just immediately put that on the stack and then call the function. Yeah, okay. And I think when we optimize the waffle, we can also very easily just optimize members that have an offset of 0 and the same size as the expression that they are applied on. We can just remove those. Okay. What else? What else? I think let's look at this. Yeah, in calls we have receivers. So in methods and method calls, in general, the syntax of having something and then doing .call some name, that was invented from the object-oriented times, small talks and the likes, and they were object-oriented in the sense that you really had the sense of objects, and they sent messages between them. So calling a method actually translates to sending a message to some object, and then the object can respond with an answer. And that's why the term receiver makes sense, because calling append on a list, you basically send some message append to the list, so the list is the receiver of that message. In most object-oriented languages, this is still called receiver actually, even if I know in the Dart compiler at least, they have the term receiver. In the Java compiler they also have the term receiver, although they don't really have the concept of messages anymore. So it's kind of a misnomer, a very historical term. It made sense back then, but now it's just weird. And especially in a functional language where you have just data and functions, and this term doesn't make any sense. Just because something is just because you call a function doesn't, the function doesn't receive anything, or it does receive the arguments. But still, I think function is a more intuitive name for that. So I'm gonna remove the term receiver from everywhere. Yeah, we have a call of a function. And the toast as well. Then in the universe, I think we just call them that. Yeah, and the waffle as well. And in the yogurt, for yogurt call, also function. That's a signature. Makes sense. Let's make sure this compiles. Yeah, I could have just renamed that up here. Well, yeah, it compiles. Okay, so no receiver anymore. Let's maybe commit that. Oh yeah. Improving Waffle readability, I guess. Hang on, something else I want to do in the Waffle is like, you know what, let's first push the renaming function, renaming receiver to function. Okay, and then I want to improve the Waffle. And I was thinking we have these suffixes like, you know, colon word or something. I think it would make sense to replace them with just the amount of bytes that something takes. I think that makes sense. Because we don't have types in this stage. So the size of something basically is somewhat like a type, I guess. Yeah. Let's see. Where do we print them here? Oh yeah, we can also do that in the member. Yeah, and a byte is just 1, a word is 8. Damn. That is pretty cool. Crazy thought. Members. Printing members differently. Just putting this down there. Look at this. I like that. Maybe it's a bit confusing. Very confusing. Kind of looks like IP addresses, you know. I'm not sure I like that. Yeah, I'm gonna keep it for now. Maybe this grows on me. Yeah, I mean, this is pretty cool, right? .0 size 8. That's 0 to 1. Like, it's very consistent. Yeah, I like that. Okay. I guess let's what should we do next? Like improve Waffle printing for some definition of improve. Right. Oh yeah, then enums, args versus payload, and tags versus byte versus symbol. So args versus payload. I think it makes sense to name them payloads. Like, most of the time I'm thinking of them like payloads, and really arguments is kind of, you know, you have an enum value and then you get the arguments of that. It's kind of, it feels a bit weird maybe. yeah, I think I'm just gonna go with payload. Then, it's a new name that doesn't conflict with the arguments of functions. So we don't have like arguments mean one thing in this particular case and another thing in that other case. Yeah, payload's fine. Oh god. Yeah, I guess I'm just going to go through that. Oh man. Yeah, so test plum, okay, I don't really care about that. Okay, so we have a tag to create an enum, and that will have payloads. Yeah, maybe let's first go through all the type definitions, I guess, and then fix the use sites after that. Yeah, lambda call has arguments, call has arguments, that's completely fine. Yeah, the tag, let's call it payloads. Yeah, lambda calls and calls, they are arguments, sure. And then ongoing type call, yeah, that makes sense. Here we have arguments. Yeah, nothing to do with tags. Yeah, call.args should be empty, string, but never, okay. Yeah, some of these, try to instantiate types, yeah, type calls, that's fine. Yeah, and here these should be payloads. Toast type variant. Toast type variant has a name and payloads. Yeah. Yeah, I think it makes sense to just go through all files and adjust the data structures and then let the errors lead the way. So in the bacon there is a concept of enums, really. In here we don't, no. No, we don't have enums. In the egg we do have them, so let's just go to the top, because that's where all the type definitions are. And indeed we have a tag in here, egg tag, that contains payloads. Fine. Yeah, there are errors below, but that's something for later. Yeah, errors has nothing to do with that formatting. Just has indentation and other stuff, sure. Memory layouts, yeah, I think this has aggregate layouts, arbitrary types, function parameters, where params, what is it? Params is called arg, that params layout, that's a to-do. Okay, yeah, but apart from that, we can lay out enums, and the variants, they have parts. Okay, that's actually fine. Lay of offsets without any, yeah, I think we should call them payload offsets. here we don't define any data structures. In here we have toast types, toast type variants with payloads. Okay, and we have toast expressions. Yeah, switch is something somewhat critical, I guess. Symbol is also, I don't know, toast call has arguments. Okay, yeah, I guess tags are just calls of symbols. Makes sense. Yeah, switch has condition percent in cases, which is a toast case, which has a symbol and payloads. Yeah. Enum types. Okay, is not named in here. That's fine. Okay, then we have universe. Hang on, we don't actually use that, do we? Nope, we don't. So let's just remove that. Remove that file. Yeah, VM has no concept of enums anymore. Waffle to bytecode. I mean, that's only like a conversion file. Doesn't define any data structures itself. Yeah, in the waffle, no enums anymore, so that's nice. In the yogurt, we do have tags, but it's just a tuple with a slice and so on. Yeah, it's good. I should turn this into like a value. I'm going to add that to my to-do list. Turn yogurt value kind into non-tuple. You know, like this could also just be a tuple of slice of yogurt value and yogurt signature, but like, this is readable. You can access the things with proper field names instead of just A and B. Okay, so a tag has payloads. Okay, yeah, that were all files. And now the only remaining thing is fixing errors. Yay. So a tag has payloads. Yeah. Amazing. Yeah, and finally down here. Oh, casting. Yeah, we have payloads. Oh, there's actually like a yogurt call. Oh, hang on. I have to be careful here. Yeah, these are actually payloads. call another cast function. Oh yeah, these are the arguments. And the payload is the argument to this function. Yeah. So this is more clear than before, I think, because you don't have the same name for the argument to some casting function and the actual enum arguments or payloads in this case. Yeah. Okay. Mm-hmm. Oh yeah, from payloads. Payloads. I'm not sure. Okay. Yeah, maybe I should have gone through this from the top to the bottom. So, from the compiler stages. So the toast first. Are there errors in here? And yes, there are. Okay, passing an enum type means we pass payloads. That makes sense. Then down here, passing a toast case. Where does that happen in here? Cases. Okay, we pass a symbol. Then the params. Let's call these params payloads. Yeah, let's convert them to a slice up here. And then from here just do that. Okay, but that's the toast. Next, the egg. Resolving names and such. Yeah, so if we have an enum, then we do some stuff. We convert a type to an egg type. I see. Oh yeah. Yeah, params is not a field on toast case. Symbol payloads body. Yeah. Yeah, and push param is fine because for the switch cases, the payloads that you define that must be there, they actually become params of the body. Yeah, so egg tag payloads is missing. Now we have a call. And we have the args. Oh yeah. If you call the tag, oh, that makes sense. Then the arguments become the payloads of the tag. It's actually like a semantic difference, a mapping that takes place there, I think. So yeah, egg yogurt, we converted that. Waffle. Yeah, just getting the payloads instead of the args. And this. Hang on, memory layout. What are you doing here? Enum layout has some parts, okay. Why is this args parts.push? Oh, this is arg. It should be payload. And let's maybe always sort the heading first in these kind of things, because I think that makes more sense. Okay. Very cool. Oh yeah, this is payload offsets. And readable code. Okay. Yeah, let's see if this works. It does not. In the yogurt, there are still errors. Okay. And that's where you convert the files from. Payloads, yeah, for each payload, we print the payload. Kinds of payloads, yeah, that makes sense. Okay, yeah, then memory layout, we have an error. Yeah, this, we want to put the payload in this place. Beautiful. Look at that. Map offsets. Cool. Yeah, and the waffle. Oh yeah, that makes sense. And that we have this in two places, because we can convert values and we can convert expressions. And this is like very short. Put that in one line. Huh. Okay, yeah. Beautiful. Rename enum args to payloads. Oh yes, these kind of refactorings, they take some time, and they're mostly like boring groundwork. But there are some cases where they really improve the code quality. Having these very strong concepts with strong names, where you immediately kind of know what you're dealing with. Then, if you have that, then most errors become obvious. Okay, so the params layout has args. That is, I'm just going through the do's and fixing them. So the params layout, hang on, that's up here somewhere. Yeah, params layout has args instead of param. Yeah, that doesn't make any sense. And then, what else? In the waffle, there's probably an error where we use that. Yes. Yeah. We want to know, put the parameter of that index there, and we have the concrete argument to put there. Oops. Nice. Okay, yeah, I'm going to do this, I think. So YogurtValue kind. Yeah, here this is like a tuple of stuff. Then let's just add proper type for that. So a YogurtTag value with a symbol and payloads. Beautiful. Yeah, and basically all the code that we touch now, yeah, should become much more readable. So this tag just has a symbol and payloads. What? Okay. YogurtValue kind dot tag, yeah, and instead of a tuple, we just put a YogurtTag value in here with a symbol and no payloads. Yeah, kind of like this. Yeah. That makes sense, but instead of a tuple, I'm just gonna use the YogurtTag value. With a symbol and payloads and similarly here. Cool. Readable. Damn. This is crazy nested. Oh, type info. Yeah, I guess. YogurtTag value of some symbol and payloads like this, I think. Okay. Oh yeah. Tag.symbol. Look at that. Yeah. Actually. More like this. Payloads is that. Very cool. Very, very cool. So, yes. Symbol is, yeah. Hang on, what does archetypes mean? Oh yeah, no, let's call them payload types. Oh, let's call these payloads. Yeah, okay, so, you know, there are a few places where we don't use args and payload consistently, apparently. I'm not sure if I want to go through all of them right now. Like the main parts that touch the actual data structures, they are fixed. The rest I'm just gonna leave, and yeah, no, they will be converted over time when I stumble upon them. Yeah. Mm-hmm. But Waffle, that's at least in the back of the compiler. So we're getting closer. Well, true. And that's actually readable, you know. If it's a payload, then we get the corresponding payload. Nice, it compiles. Okay, yeah. So I guess rename, like create tag, YogurtTag value. Cool. Next. Tags versus byte versus symbol versus variant stuff, like what is what, basically. Yeah, that's kind of difficult. Like enum is a type, basically. Whoa. A type with variants, and each variant can have a symbol and payloads. Yeah. So then the question is, what are tags? Oh yeah, and I think tags are just like comp-time values when we don't yet have types, something like in the egg, you know, you create a sum 5. Then the act of creating that sum value is basically a tag. So an enum type, the instances of that, when you create them, they are called tags. But that's also variant, right? So could just call them variant. Yeah, I think remove tag and instead have variant. Or rather, like keep tag, but tag is only in the waffle, in the memory layouted part, the byte, basically. Yeah. Okay. So tag is basically just a byte in. Okay. Enum is a type. Has variants. Variant. Each variant has a symbol and payload. Payloads, plural. Okay, symbol is just a string. Yes, and then there's a tag, which is a byte in the tag union. That makes sense. A tag union being the aggregate that contains some payload and then the tag. Okay, so I think I used tag in some previous compiler stages currently. Okay, in the yogurt apparently. in the Waffle, where that kind of makes sense, I think. Okay, yeah. So we have, okay, compiler stage, that is nothing relevant. Oh yeah, and in the egg, this is, let's call this variant, because really this creates a variant. And then they can be joined to enum variants, to enums that have then multiple variants. That makes total sense. Yeah, better than tag, I think. Yeah, so these are really called variants. And then you have the variant payloads and the variant symbol. Yeah. Nice. Yeah, memory layering, I'm gonna get back to that. And the Waffle first. Yeah, and the yogurt. We don't want tags, but instead these are variants. Yeah. Just because that's exactly what a variant is. Something with a symbol and payloads. That's on the type level, where enums can have variants, and that's on the value level, where you have one concrete variant. Okay, so this will just be variant. YogurtTag value. No, that's variant. You would opt in variant with a yogurt variant. How does that exist? Yeah. No, it does. No, it does. Okay, yeah. Yeah, that was the entire yogurt. Yeah, then onto the Waffle. And here we don't have variants anymore. Yeah, because enums have been converted into tagged unions. So if we encounter a variant, actually fix that. Oh. Nope. Oh, sorry, in here it's a tag, yeah. The memory layout can either be padding, payload, or the tag, which is the actual byte. Yes, tag with a byte, tag with a byte. Yeah, this is like tag to variant. Tag to variant. That is to the symbol, right? Hang on, the layout of tag to. I'm gonna have to look at that. Same here. Tag offset, okay. Yeah, so tag offset makes sense. Tag to, layout tag to variant. Basically tag to symbol, really, but I think variant makes more sense here. Maybe. I'm gonna leave it like it is. Amazing. Amazing. Okay. Yeah. So let's see if this compiles. It does compile. Make enum terminology consistent. Yeah. And I think it makes sense to have this terminology inside the compiler section. Enum is a type, has variants. Variant, symbol, and payloads. Either on type or value level. Symbol, string, indicating a variant. Tag is a byte in the low level tag unit. Okay, yeah. And also like for functions, the difference between arguments passed to a function at a call. Accepted from a function. Yeah. At a call, we passed arguments, the values become parameters. For the function. Yeah, something like this. Okay. Yeah, this doesn't really fit in the README. I guess let's have some notes document for that. With notes. Oh, I should also update the README. Oh man. Yeah, so this part right here. At least the switch syntax should be updated. Nice. Okay, yeah. I'm gonna take a break. And then we'll just see. Okay, next. I'm gonna try to make recursive types work. Yeah, because that's something that's a bit more complicated. Let's just see what happens if we have a recursive type. So let's say, we have some function, we have a recursive type called foo. It's a struct that contains an a and a b, which is another foo. Okay, and then we could say, this returns foo. Or maybe this calls some function bloop with a. Bloop a with an int, and that is supposed to return foo. Now the thing is, this is a recursive type, and it's basically a struct. And you can never create this. Because in order to create a foo, you need an int and a foo. So that doesn't work. The only way to really make recursive types work and make them useful is if there's an enum somewhere in them. So for example, lists. Here, a linked list of t is either empty or it's more, with an int and like a t and the rest of the list. Yeah, let's not deal with this for now. I'm actually not sure what's supposed to happen in that case. Is that, is this a compiler error, or is this just valid, but you can never create that? I think both of those are same behaviors. Yeah, but for now let's just maybe create a list and see what happens. So a list containing one item. I think that's fair. You can still return and just create a list and then return 0 and ignore the list. Let's see. Oh yeah, foo doesn't exist. Okay, sure. That's true. Yeah. Oh, unreachable. Interesting. Waffling list of int. So what we do is we call toWaffle on something, and then we want to calculate the memory layout of an enum. And that means we need to calculate the memory layout of the enum variants, and that means that we basically reach some recursive type apparently. Let's see, unreachable is what it says. Fun memory layout. Yeah, here recursive types, we say, hey, they can never be reached. And that's not correct, I think. Or maybe it is. I don't know. Basically, yeah, I think this is a special, like this only applies to enums because, structs are not allowed to be recursive. If you have some recursive type, then there must be an enum somewhere in that recursion chain. Yeah, and also we don't want to favor if we have like mutually recursive enums, we don't want to favor one of these enums over the other. So I think if you have an enum and if a variant of that is recursive, then we just want to save a pointer in there rather than inlining the value, which would then again inline the value and again. And so we can't make enum types arbitrarily big. So we want to limit their depth, I think, or like while memory layouting, we want to check, hey, is this enum variant recursive? And if so, then we treat that specially. Okay, so layouting enums. If we have a recursive enum, then we actually need to treat that differently. Like the Waffle code we generate for that will be different. We will need some malloc calls, and when traversing into that, we will need to dereference stuff and like access memory and store things there, and do all like crazy things. So I think we need to make this a bit more complicated. Yeah, the variant layouts, because the parts here, oh yeah, they can be padding, they can be the tag, a payload, but it can also be a pointer to a payload. Yeah, like an indirect payload, I guess, or like indirect payload. Yeah, let's call it that. Same as this payload basically. The int has the same meaning. It's just the index of the payload within this variant, but saved behind a pointer. Yeah, let's maybe the payload saved behind is saved on the heap behind. Saved on the heap. This is only a pointer. Yeah, that's basically what this means. We could also just call it payload pointer. Right. So memory layout enum, what does that do? For the variants, we lay out the arguments. Yeah. And I think in here, we basically need to check if the argument is recursive. So I think there is this, is recursive with a depth. If arg is recursive. We always want to push something. This just determines what kind of thing we want to push. Yeah, so if arg is recursive, then we do that. Otherwise, we had a memory layout and of a pointer, which means size 8, alignment 8. Yeah. And then we lay them out. Okay. And down, yeah, that still makes sense. And then we have the variant layouts. Oh yeah. So for the fields, we basically need to check, is this field recursive, yeah. I mean, this is not super efficient checking again whether that's recursive, but I mean, let's maybe pull this out into some, or I don't even know. Indirect variants. But then again, it's like per variant we have a separate. Yeah, I'm just keeping it like this, I think. Yeah, sure. So for a field of some index, we basically can do that same check again. So we can do like if variant of value, which are the payloads, get the payload at that index. Yeah, if that is recursive, then this is going to be a variant part of payload pointer of that index, else it's just going to be a normal payload. Yeah, something like that. And then of course we need to handle that when converting to a waffle. So I think this is in the what's in waffle directly. Okay. So yeah, if we have payload pointer to some index, you know what? Yeah, let's change that to the more succinct version. Yeah, there's a payload pointer. Okay. Yeah, then we just do this kind of. Well, you see, this is really difficult. So we have some sort of waffle expression. But basically we want to push some value onto the heap, which means now we have to do like crazy, like really complicated stuff. We have a variant. We can get the value at that index. Okay, so let's maybe get the value, like the payload maybe. And then that payload will be some value and a type. Convert that to a waffle, which will be a waffle expression, and it will also give us I think basically we need to. It's fine that we convert this to a waffle, but then we need to store that waffle expression on the heap. So we need to allocate memory. Like, I'm not even sure. Hang on. Waffle expressions. They can be. Can they be a body? No, they can't. Okay. Interesting. How are we supposed to do that? In the bytecode, there's a malloc, malloc instruction. In here, we have no way to to do something like that. We could just have, put this on the heap, basically. I think that makes sense, actually. Some sort of boxed waffle. Which basically constructs this waffle expression and then allocates memory for it on the heap and then evaluates to a pointer to that memory. So this is a boxed waffle expression always has a size of 8 and alignment of 8 because it's just a pointer. But I think this is kind of weird. Hang on, we don't have these like store and load operations either. Like how do we even do that? I mean, when lowering Waffle to bytecode and we see that something is boxed, then we can just calculate that and then put, then basically emit malloc instruction and several like store instructions that store the correct things on the stack, on the heap. And that would work. I think that makes sense. Yeah. Let's call it box, maybe. And unbox would also be a thing. Yeah, and converting these to bytecode is another topic. Yeah, but I think that makes, at least conceptually, that makes sense. Okay, so if we have a box of some expression, it would actually just print box of that. And same with unbox. Yeah, let's say this also prints the size. Yeah, because this will just be pointer. So 8. No, here it doesn't make sense to print the size because this is just a pointer and there's nothing like interesting or special about that. Every box is just 8 bytes. But in this case, unboxing, the size is kind of important. Okay, so we have that. This becomes reasonably doable, I think. Let me get to the constructors for all these things and add a waffle box constructor of some expression. It's going to return a waffle expression with size 8, alignment 8, kind waffle expression kind dot box of expression put on heap. Yeah, pretty similar the unbox will just will take a size and an alignment, and then it will use those and result in an unbox expression. Cool. It's kind of ironic that the box is very similar to this put on heap function that we have. It's basically just going to be that, you know, you have some value and then you're going to convert that into a reference to that value, like a pointer. So payload pointer, in this case it evaluates to nothing. Yeah, we will just take the waffle and then say waffle box. And sure, yeah, let's just inline all that. Sure. Very cool. Yeah, when creating a variant, there's something as a pointer, then yogurt id to waffle expression dot get variant payloads. Sure. And then we create a waffle unbox expression of that. Unbox that, please. Waffle yogurt ID to waffle expression is not in scope. Oh yeah, makes sense. But the errors are still catching up, I think. Oh, maybe not. Oh yeah, because this also needs size and alignment. Index. Hang on. Here we get the index, like the payload. I think then we can just say get the payload. This is a yogurt ID to waffle expression. Yeah. You can also do like fun payload ID, payload expression is fun to get payload ID. Like this is the yogurt expression. This is the waffle expression. And then we unbox the waffle expression. And the size is the yogurt expression's size. Oh no. Payload layout is payload yogurt expression dot type dot memory layout. Yeah, something like this. Damn. Sure. Wondering that there's no error on the switch, but I guess we'll get to that. Okay, we have a waffle. Damn. That is kind of crazy, actually. So let's see. List of int. Creates amazing an aggregate containing the int. And what is going on here? An int and the tag 1. And then Well, that probably makes some sense. I don't know. I mean, what is this gonna be? Yeah, this is an enum with 2 payloads. Oh yeah, this enum only has 1 byte for the tag, nothing else. This is just 8 bytes. And this entire enum also has 1 variant and 1 byte. Okay, so this is probably what this is. That makes sense. We create the empty instance, which is just a tag, tag 0. And then this right here is the more of, this right here, more of int and empty. So this signifies more, 1 byte, one tag, of int, the argument, and empty. That makes sense. And then we cast that to this more generic recursive type. Okay, so we have this size 10, because 8 bytes for the int, and then 2 tags. And what we do is we get the entire thing, like offset 0, size 10, and then we get just the last byte of that. Yeah, that is guaranteed to be 0, because that's just the more variant. So what we do is, in the end, we just create an aggregate of some other stuff with a 1 at the end, because empty comes alphabetically before more, so more has byte 1, like the tag is 1. This indicates this is a more thing. Amazing. Okay, and then what we do in here is kind of weird. So first we cast the int to an int. I mean, sure, you can do that. Let's see, we take from the argument, 0 the entire thing, and then offset 0 size 8. Yeah, that basically cuts out the int from this aggregate. And then we cast that empty thing to, this. We call that, right? Where's that defined, by the way? Down here. Casting an empty to an empty of that. So we take the entire empty, which is from 0 to 1. Then we take the tag of that, which is also offset 0, size 1. And we switch on that. The only possible thing is the empty part. Ooh, and then we create an aggregate that contains padding 16 and then 0 and 1. So apparently the size of this here is 17 bytes. 1 byte in the end for the tag empty, and then this is 16 bytes. Oh yeah, the tag that tells us whether it's empty or more. And empty has no payload, so it's padding 16, but the more would have 16 payloads, because it's an int 8 bytes and then recursive type, which becomes a pointer, which is also 8 bytes. Amazing. That is actually amazing. Okay, so this works. We cast the empty to that. Get back something with 17 bytes. And then, this is exactly the wrong way, I think. Hang on. Waffle unbox. Did I create the unbox? Did I use that? Waffle unbox. Oh, I see. Well, and this is just supposed to be a box, right? Well, that's much simpler. That is much simpler. Yeah, true. When we create a variant, then we also want to put that on the heap, box that. Yeah, let me just inline a bit of this and format it a bit more densely, and then, yeah, run this again and see what happens. Okay. Oh yes, this is much better. So here we call that function that returns this, 17 bytes long enum thing. And then in here we create another 17 bytes long enum thing. Because it has the same type. So these are compatible. But this time the tag is a 1 to indicate that this is more. And instead of 16 bytes of padding, we first have the integer that we want to save. And then basically the recursive part, which will be a pointer to this expression right here. Yo, that is amazing. So basically what this tells us, hey, please allocate, please construct this value, which just consists of padding and some stuff, and then put that on the heap somewhere, box that. But by the way, box box is a weird name basically, but it's like allocating space for that on the heap and then storing a pointer to that in here. So a box is like a reference to something, I guess. Yeah. It's a weird term now that I think about it. It's basically the common term for this in compilers. Like, compiler people often talk about like having unboxed values, for example, if there are no pointers, and boxing things and unboxing things. But it's a weirdly general name for such a specific concept, now that I think about it. Anyways, we boxed that, so we put it on the heap, and yeah, so the resulting thing also has the same memory layout as this one. 16 bytes and then 1 byte of some tag. Okay, that's amazing. Next, what can we do? Here we just call that cast function. Okay, yeah. Switching should work with that. I'm really wondering why the switch doesn't yell at us for being wrong about something. Oh, yeah, this is just printing, but the actual switch down here. Let's maybe first create a simple example that works with that. So we have foo, which is a list containing only the A. And then, we could just do it like this. And then we switch on that, and if that's empty, then we return 0 if it's more of some foo. And the rest of the list, codons, I think. Then we'll just return the foo, which should be an int. In fact, it should be the int that we passed in before. Okay, so now things don't work. That's basically what I expected. Something was supposed to break. So here we switch on this enum. And we compile the main function. And here we try to access these things. The problem is this this expression right here is only 17 bytes, like we saw before. And yeah, this is an int, and this is something bigger apparently. And I think we need more information about when we get the payloads from an enum. Yeah, so right now each variant basically has this variant layout, which has parts, which you need to respect when constructing that variant. And when accessing things, we just have these payload offsets. But actually this should be like indications of whether it's saved unboxed or boxed. So I guess we need some variant payload. Variant payload. How do we call that? Like, we could put offset in the name somewhere. Basically, I want to save an int and whether it's boxed or unboxed. Maybe something like this. Boxing. And boxing can either be boxed or unboxed. Something like that. Or I put the int directly, like I basically have an int in here and an int in here. But this seems like, I think for now this is fine. Yeah, okay. So it's not really the offsets, it's basically the payload, where to find them, basically. Yeah, and that's the offset, and whether they are on the heap, like boxed. Payload positions, I guess. Yeah. Oh yeah, and then let's maybe have this struct payload position with an offset and a boxing. And then in here, instead of the tuple, because tuples are really like, you should have used something better there. We have these payload positions. Yeah, that makes sense. So payload positions. Is a slice of payload positions. Yeah, and for each field to offset, we do something. Yeah, that's correct. The payload position will be something with an offset and a boxing. And the boxing is, whether that field was recursive. It is weird that we have this in like 3 different places right now, and they have to be kept in sync. I don't like that at all. I think I'm gonna add a variant to boxing, maybe. Map from string to boxing. And like for each variant in the variant names. Yeah. Basically get the get the type of that via variance get variant. That gives us a type. We can check is that recursive, and then this will be boxing dot boxed else boxing dot unboxed. And this is what we're going to add to this map. So variant to boxing dot put under that variance this thing. Yeah, that is at least a bit more explicit than, is this recursive? And having these recursive checks in here all over the place. So variant to boxing. Ooh. Oh yeah, we can even switch like, is this boxed? Then that's a lot more readable, I think. You don't have this, just switching on true and false, but you have very explicitly, if it's boxed, then we won't have this. If it's unboxed, then we have this. That's nice. Yeah, and same here. So if hang on, we have the index, I guess. Yeah. What do we do here? Oh, hang on. Hang on, this doesn't make any sense. Because the variants themselves, they are not boxed or unboxed, but their payloads are. Yeah, so variant, this is actually a slice. So I think we want, okay, it's getting a bit ugly. Boxing, sure. Let's say that's a list of boxings, and then for each payload in variant.get variant, if payload is recursive, then that's boxed else unboxed, and that is what we add to the boxing. Something like this. Expected do keyword indeed. Yes. So boxing convert slice will be that. Okay. Yeah. Yeah. For each variant. Yeah. So here we can do variant to payload boxing dot get our current variant. Yeah. Not super beautiful, but meh. Get variant, and then we get the arg index from that. Okay, and down here, something similar. I'm gonna call this like boxings, stuff like that. And I'm gonna copy that down here as well. So get the layout. Hell yes. And we get the boxings, which is that. And then in here we can say yeah, boxings dot get at that index. We switch on that. Yes, that is like the semantic, like this is code that is on the semantic level, where you don't deal with bools or stuff, but yeah, that's super nice. Okay, and then finally, down here, we can check the boxing, which will be, oh, we're still in the variant thingy, which means we have access to the boxings. That's amazing. Boxings dot get, well, entry dot, hang on, key, which will be the index. Yeah, that makes sense. Okay. Nice. What's going on here? Variant to boxing. No, it's called variant payload boxing. Boxings is what it actually should be. Yeah. Just call this one. Okay. Because get oats is map entry. Yeah, I guess. Okay. Let's guess variant key. And yet another error down here. Layout position is what it's called. Oh, same here. Cool. Then we need to handle that in the waffle. In the switch. Yes. Nice. Yeah, let's maybe think about this. So our enum payload is some memory region. And yeah, basically if we find, if we just want a waffle member, we can what can we do? I think we want to take a member in either case, right? But in one case we want the member, we want to just get the pointer basically. The member is just a pointer, and then we want to unbox that member later on. So I think in here we will need to do something like this. Payload positions get, yeah. Maybe let's say payload position is that. Payload.index, okay. And then in here we can say if switch on payload position.boxing, and if it's boxed, then we do one thing. If it's unboxed, then we do what we basically did before. Then we just get a member of the payload position.offset with the size and alignment, because then the payload is stored directly inside of the enum value. Otherwise, we want to basically do a waffle unbox. So first we want to I think we want to do this. If it is boxed, then this condition, aka this enum that we switch on, at the offset, it actually just contains a pointer. So we get that pointer, which has a size of 8, alignment of 8, and well, we unbox that pointer, loading the memory that is stored at that pointer, and that should be of the payload. That should be the actual payload of the size and alignment that we expect. Okay, it compiles. Damn. We have some stuff in here. So we create a list. Let's maybe look at this. Yeah, this is the same as before. Makes sense. Now we switch on that, and we get, if it's, hang on, this is empty, right? Yeah, if it's empty, then we just return 0. Okay, yeah, that makes sense. If it's 1, then we get at offset 0 something of size 8. We get the int that is directly contained in there. Okay, that is too optimized. I mean, it is correct. It is correct. It just doesn't help us test the unboxing. Because of course, if we have an enum list, then the int will be contained directly in there. Yeah, let's do a more complicated function maybe. One that calculates the length of a list. So let's say this foo, and then we take foo.len, not .len, but piped into len, or something like that. Oh, okay, but that's like completely different. Is there like, let's write our own len function maybe that doesn't do any addition, and that is not correct, but at least it is recursive. So if it's empty, then it just returns 42, and otherwise it returns the length of the rest, which will be 42. Stupid. Yeah. Still, okay. Why is that happening? Stupid. We don't do any addition, do we? Oh, here we say len. Oh no, it's stupid len. Fair. Okay. Okay. Yeah, this looks pretty amazing. Okay, so let's see what we do. We get an enum that is either empty or more, containing an int and recursive thing. And as we've established before, this is 10 bytes. Hang on, no. 8 bytes, 60 bytes, 70 bytes. Yeah, 1 byte for the tag, and the payloads of the more variant are 8 bytes and another 8 bytes, so 60. Okay, 0 is an aggregate containing the arguments. So from that aggregate, we first get the first argument, which is the entire aggregate, because, so offset 0, size 70. And then we get the tag of the enum, which is the last byte. At offset 16, 1 byte in size. And we switch on that. If this is an empty enum, then we return an int 42, 8 bytes. Amazing. Otherwise, we call stupid len. Crazy. And the question is with what? Well, we take our argument struct, the entire thing, and then at offset 8 with a size of 8, there's the pointer to the next list item. And then we unbox, aka dereference that pointer. Oh, of the size 8. That's not what I expected. Of the size 8. Now this should be 17. Okay, so here we do that by getting the payload layout. So fun get ID. We get the expression and its type. I mean, this should be a self-contained type, right? Let's just add some debug logging. So let's just save this entire thing as layout, which we later return, but we also print that. Type as size, layout with size. Okay. So int of size 8. Okay. Yeah. This enum has size 1, size 1. This has size 10. Yeah, 8 plus 1 plus 1. Recursive thing has size 17. Perfect. Yeah, that was the list function. Then we have the cast function, that's also correct. And then the main function. And apparently there is something, oh no, the stupid land function. This has, there's an error somewhere in here, probably. So int has size 8, that's correct. This has size 17, correct. Well. I don't know what to do with that. To be honest, like case unboxed. I mean, yeah, unboxed should be correct. And the boxed thing gets the pointer from inside the struct. With size 8, alignment 8. Okay, and then it unboxes that with the expected size. It looks so correct. Now let me put that unbox, that we don't do anything stupid here. I don't think so. No. When writing that, expression.size. Oh, no. Expression is the inner expression, which will always be a pointer. Oh yeah, by the way, like fun, waffle, unbox. Yeah, we have this with size and alignment. We should also assert that the expression size equals 8. Expected pointer. Yeah, okay. So we don't want the... What exactly is going wrong? Yeah, we don't want the shadowed version. This right here. We want the outer expression. Yeah, that's the thing. So basically we have this pointer, I guess. Yeah, and then here we take the expression. That makes sense. So just a printing error. Right. Oh, amazing. So we have this pointer in here. We unbox that and get 17 bytes from there, and that is what we return. Oh no, then we call stupidlen with that, and that returns something that is 8 bytes in size, and that is what we return. Okay, amazing. What? Okay, so we can now save recursive enum variants. Yeah. Oh yeah, actually, maybe we should add. Like for the structs, if we have recursive structs without enums in between, that should be an error or handled somehow. So let's at least add a to-do somewhere. So some memory layout struct. Think about recursive structs. Error. Allow by no data. I don't know. Something. What, like the never type? Yeah. Okay. Yeah, because we just changed the waffle by adding this box and unbox thingy, we do need to fix the conversion from waffle to bytecode. So if we would enable that down here, you know. Where's that? Waffle is this apparently, sure. But yeah, if we say waffle to bytecode and then we print that bytecode, this will probably, not work. So in here we switch on something. Oh yeah, struct was renamed to aggregate. That's like a completely different issue as well. Sure. Yeah, but box and unbox are not handled. So should do that, I think down here. Box some enum expression. Yeah, and let me just check what the malloc thing does. It pops an alignment 8-bit, a size 64-bit, and pushes an address. Okay, and all these store thingies, they first pop the data and then the address. So I think the first thing we need to do is allocate memory for that inner thing. Right. I'm actually not sure. I mean, how does it should be pretty similar to like copy from stack or something, or like we had something like that. Yeah, copy from stack. Yeah. And it should be similar, but okay, so I guess let's first compile the inner thing. Like the inner thing is an expression, so inner.compile with the builder. Yeah. These are kind of, the order of these is somewhat difficult to deal with. I think. So, you know, the load things, they are really nice, because if we have an address, then we can just basically load an entire like complicated struct by pushing the address to the stack, you know, and then calling load 64, for example. That will pop the address, load an int from there, and push that to the stack. And then we can put the address on the stack again, and that will, and again, call load, which will consume the address, pop the data instead. And we do that again, and basically we just, you know, copy something from the heap to our stack. But for the store thing, it's kind of difficult, because this assumes that the, you know, that the byte and the data lives above the address. So this is not like the reverse thing. Yeah. Which means if we have some bigger value on the stack and we want to push that into the, you know, into memory somewhere, into the heap, then we can't just push an address and then say store, and then it consumes some back part of this, like the end of the struct. And then we push the address again and again and again, and just piece by piece consume this struct and, you know, put that into memory. But instead we have this huge struct value somewhere, and then we need to get push the address on the stack and push some part of the struct on the stack again, and then say store that, please. That gets stored. Then we push the address to the stack again, push another part of the struct, and say store that, and basically get all of the struct data, copy them to the top of the stack, like 64 bits at a time, and store them separately. And only then, when we have stored that entire thing, we can push, pop the entire struct at once. Yeah, that is a bit more wasteful, I guess, whatever. I don't know, it's a bit more inelegant, I would say. Yeah. But I guess it's fine for now. It is fine. We can deal with that. Okay, so we compile the inner thing. Let's maybe save the size, or like not the offset, but the struct, like data start, I guess. And that's just the builder stack size. And then we have the inner thing, which means we compile the value. Okay, so the value is somewhere on the stack. Sure. I'm gonna call it data. I think that's fine. Okay, now we want to allocate memory. So we need to emit the bytecode instruction, malloc. And this instruction expects two other instructions to be on the stack, namely the amount of data to be malloc, and that's the data size. So that's an expression, so we can use size. Yeah. And also like padding. We need to do padding. Get that data. And also the alignment should be there. And that's the alignment of the data. We call malloc, which consumes these things. Allocate memory for the data. Compute the data to be boxed. Allocate memory for the data. Copy the data to the heap. Amazing. Yeah, what that does is basically we walk over the data. Yeah. So data, not data offset, but cursor, I guess, is 0. Yeah. And then we loop. If the cursor is less than data.size, yeah, cursor plus 8 is less than data.size. And if that's equal, that's also fine. Yeah. But if it's more, then we want to break. Else we do some stuff. And then we say cursor is basically cursor plus 8. And yeah, I'm gonna add a to do in there because I'm first going to do the last part. So, if cursor equals data size, then we're done. otherwise we're gonna copy 1 byte. Well, okay, we're first going to copy the like address start or something. It's gonna be here, address start, yeah. And then we do, well, address start is builder dot I mean, at some point we want to emit this store 8 instruction, and that expects an address to be on the stack and some data to be on the stack. So we first need to store the address on the stack, which is the, you know, stack size minus address start, or like plus 8 or something, something weird. This is 8 bytes, so this is minus 8, I think. Okay, and then we also want to push 8 bytes, like push 1 byte from the stack, which will be at builder.stackSize minus data start plus cursor minus 1. Amazing. Right. So then the most, like the more efficient case up here, maybe, would do something similar actually. It would, oh, by the way, here we need to do cursor equals cursor plus 1. Yeah, here we first push the address from the, hang on. We need to add something. We need to add the cursor to that address. Ooh, yeah. So this will also need builder init bytecode instruction dot push 64. The cursor, and then builder init bytecode instruction dot add. Oh, this is, I'm not gonna say bloated, but it is something. Okay, sure. So yeah, we've done that. Then we want to push 64 bits from the actual data. So push 64 from builder stack size minus data start plus cursor minus 8. Okay. Yeah, that seems correct, I think. And then finally, we want to emit the bytecode instruction that store 64. Damn. Okay, and for this to yeah, like this works for an alignment of 8. We may need to do something else if the alignment is not 8, because then this might actually be, let me just comment this out for now and just copy bytes over individually, and then we can optimize the data. Okay, yeah, but that's basically box. Oh man. Okay, I think unboxing is a bit easier. So unbox of some pointer. What will that do? Well, I mean, let's call this not address, but pointer start. And then this is very similar to this. Like we have the pointer start, which is the builder stack size. -8, basically. Oh no, hang on. Yes, it's exactly this, and then we compile the pointer first, because the pointer itself may be something deep inside from another struct or something. Okay, so data.compile builder. Yeah, this will be pointer.compile builder. Now we have the pointer on stack. Okay, yeah, and then we basically do something like this. Copy the data from the heap. So we'll have a cursor, compute the pointer, unbox to copy the data from the heap. We'll just do this. So if the cursor equals the data size, then we break. Okay, yeah, otherwise we do builder.emit of some bytecode instruction dot. And how does the load look again? Load 8 for now. Pops an address, loads a byte from that address, and pushes that byte. Okay. Yeah. So we take the stack size minus the pointer start, which will give us, well, we'll push the pointer on the stack. Yeah, to do align is something we need to do up here. And then builder.emit. Yeah, we push the cursor, we add that to the pointer. We emit the bytecode instruction for pushing 8 from the stack. Nope, we don't have anything here. And instead what we do is we push the load 8 instruction, which will consume this entire thing and just load the byte at that address. Yeah, and we need to care about alignment here, so yeah, true. Okay, but I think like in general this should work. Yeah, data alignment, yeah. Unbox the pointer if that is, look at that expression dot size in this case, not pointer dot size. Okay, that is something. Crazy. That is honestly crazy. Yeah, let's maybe do something. Oh, we can't do something simpler because we need some complexity to make the compiler generate that heap code. Okay, but we basically have some function apparently. I mean, okay, all of the emitting calls, where are they? Yeah, let's remove those. So that we have a chance to see the waffle. Oh yeah. So I think the first one is this. Right. Yeah, I think they are compiled in the same order as they are printed, because that's deterministic. So we have a list of int. So what we do is we push 64 from stack at position 0, which should be the int. Okay, we call some function that is 6e60, which is above this. That does not seem correct, but okay, I guess. We push some padding. Oh, is this a main function maybe? Maybe that could work. Like pushing something, then calling another function. But this will like push padding 7. That's weird. That's weird. Oh, no, it's not. It's not, because list is yeah, list returns something with 17 bytes of length. 17 bytes, so we push 7 more bytes. So the stack is 24 bytes in size, 8 bytes aligned. Okay, then we push, this seems correct as well, I think. Oh yeah, copying the list. So copying the first int, then copying the second, like the pointer basically, like the payload of the enum, of the list enum, then pushing the tag, where the offset is bigger because we added these 7 bytes of padding, and this is not like, yeah, like implicitly if you add 8 to this, you get to 24. You get to the start of the 64. The start is 24 bytes back. Same here. And here if you add 1, that's also 24 bytes back. So these all copy the same region, like these 3 things that make up the list enum. And then we call this list len function down here. Amazing. And that consumes this and does things and returns the list length, like an int, either way. Yeah. So then these 32 bytes, yeah. So 24 bytes of this, and then we skip the top thing. Oh yeah, this is already, like this is consumed by the call. Oh yeah, and then this and these 24 bytes. And that already like these bytes basically, these 32 bytes get popped, and then the argument of this function also gets popped. So the only remaining thing is this length, and we return. So that means that this will be the list length function. The list length function. Oh yeah, that's the actual interesting part actually. That's cool. So what it's going to do is it's going to push. I think it makes sense to like draw that out. Yeah, I'm gonna. Blah. Come on. Yeah, I'm gonna add a new tab for this. I don't know, can I make this smaller or bigger? I can't. Okay. So the list len function, like, you know, what was it called? Stupid len, of a list, aka an enum that is either empty or more with an int and a recursive type. So this enum right here has this memory layout. First, payload. I'm not gonna get into that. And then either 0 or 1. And yeah, the payload is actually not this, but it's gonna be, you know, for the empty variant it's gonna be this. For the more variant it's gonna be that. The empty variant is 0 and just contains 16 padding bytes before that. And the more variant looks like this. It has an int. Yeah. An int and then a pointer. Yeah. The memory layout kind of looks like this, you know? 16 bytes of padding and then 0 byte, or this and then 1 byte. So what does it look like in our case? In our case we call the list of, I think 2 or something, or 42 or something, you know, of the argument that the main function gets. And that means we have the more variant. So let's say we called list like main of 5. And that means that we called list of 5, which creates more of 5 and empty, and casts that to this type. And that means it's gonna allocate memory somewhere. So somewhere in memory, like let's say at address 0x10, let's say, we have this in memory. Yeah. We have this. And at this place we have the empty variant. So that's actually just going to be 1, 2, 3, 4, 5, 6, 7, 8. Something like this. 17 bytes of zeros, or like padding can be anything really. Like you could just as easily say, hey, these are like invalid, just some padding, whatever happens to be there in memory. Okay, so when we create a list of 5, actually we get back this more thing. And that more thing has first the int, so the 5 in little endian, which means the 5 is in the first byte. and the entire int is 8 bytes. And then we have a pointer, also 8 bytes, to somewhere in memory, to this address right here. So a pointer to that address. And then we have a 1 to indicate that this is the more variant. Yeah. So this is the stack that we have when we start here. And you can see the first thing we do is we push 7 bytes of padding. So 1, 2, 3, 4, 5, 6, 7. 7 bytes. And our stack is aligned to 8 bytes. Then we push a 64-bit integer, aka 8 bytes, from the stack at offset 16. So 1, 2, 3, 8. 8 is here, 16 is here. And then the 8 bytes below that. So this 5 is actually pushed down here on the stack. And then we do that same thing again, but now 16 bytes means refers to this one right here. So we push that on the stack. And then at an offset of 23, we push 8 bits, aka 1 byte. So you know 16, these would be 24, these are 23 bytes. And the byte below that, this one, we push that to the stack as well. Next, below the top byte, we push 16 bytes. So let's do that. We have the top byte, and then the 16 bytes below that, we pop them, like this. And then we have this jump table, which says, look at the top byte on the stack. And you jump to that body. So if the byte is 0, then we jump to this. If it's 1, we jump to that. And those should be the only 2 options right here. The byte is 1, so we actually do that. We push, we jump to like 9910, which will be here. Basically what we just checked is that we have the more variant. Because again, this is the tag of our enum that tells us this is more. Yeah, the jumping will actually consume the byte. So boom, the stack is gonna look like this. We consumed the byte, and now we are here. So we push 8 bytes from the stack at offset 16. 16 bytes, 8 bytes above that is this. And then we do the same thing again, 16 bytes and 8 bytes here. And oh, I see a pattern. Yes, same thing. So we get the push 8 from stack 23. 23 is this. Push 8 means we get this 8-bit byte. Push that. And then we pop that again. Pop 1 byte, boom. And then we skip the top 8 bytes and pop the 8 ones below that. So we keep these bytes, the address of our struct, and we pop these. So now we only have the address in here. The address that refers to this other part. The other, this is basically a linked list. And the first node of the linked list is on the stack and has a pointer to the second inner node of the linked list, which lives somewhere in memory. Just contains padding and tag. So what we do now is we push that address again. Offset 0 is what's directly on the stack, so we duplicate this. Boom. And then we push 0. Let me just copy that and then add this to 0. Okay, then we add those. So we add 64. And that will consume these two. Boom. and produce their sum. Yeah, and then we'll load the byte at that position. Turns out that's this padding byte right here. Oh yeah, and load also consumes this thing. So we have the first byte. Oh shit, yeah, and this basically continues for all bytes. So, yeah, push, load byte, okay, and then we push the 64 from the stack at offset 1, so offset 1, and then these 64 things, pushing them to the stack. And yeah, this is, like, the alignment is not working properly yet, so we will need to fix that somehow. Yeah, and then pushing a 1, which will now actually be like 1 and then some zeros like this. And yeah, the stack is unaligned. We need to fix that. Yeah, we add those two. So basically resulting in this. And then we load a byte from that. And now the address is 11. So we're actually going to load the second byte. Boom. And then we do the same with the third byte, fourth byte, fifth byte, and like basically all the bytes in here. And then I assume we do some other stuff, but yeah, we can't see that. Probably because in here we just hard code allocate memory for some fixed size, right? Yeah, 200 instructions. Those are not, are those 200 instructions? Maybe. Same thing. What? Oh, I think in the main, main plum file, we only print. So let's maybe print 200 and see what happens. Okay, so this looks good. This means there's basically 0 bytes here. So okay, yeah, you can see like the pushing continues until we've added 16 bytes. We load that, aka the 17th bytes, because the bytes are 0 indexed. And that means that after this load, we will actually have copied the entire memory region here on the stack. So the stack is gonna look like this. That's cool. So what we do then is, I think we call ourselves recursively and CB40. CB40. Yeah. Here was the main function, and this was the stupid len function. So we call ourselves recursively, which means, well, we're going to push 7 bytes of padding. Then we push a 64 from the stack at offset 16, offset 16, then there's this. Yeah, pushing that, and then pushing offset 16, next padding, pushing a byte from here, boom. Then popping below the 16 bytes below the top byte, so top byte, 16 bytes below, like this. And then we again have this jump table. But now the second node in our linked list will actually have the tag 0. So here we jump to CBD0. CBD0, that's directly this. So we've jumped there, and the jump consumes this byte. So we push 42 here. So this is hexadecimal, so this would be 2A, I think. And yeah, zeros. And then we push that same thing again. I mean, sure. Below those top 8 bytes, we pop these 8 bytes. This can definitely be optimized. And then we jump to this 11D368. 11D368, right here. Push 64 from stack at offset 0. Boom. And pop below the top 8 bytes we pop 15 bytes. 15 is a weird number. So basically these bytes right here. And that's 17 bytes, so 16 plus 1. Like this. Yeah, I guess. And then we return. What do we return to? Well, in the first version, we loaded all these. We basically loaded the node from the heap from memory, put that on the stack, and then we called ourselves recursively. And now we've returned, and we continue executing here. So we push the byte, this pointer, we push that. Okay. And below the top 8 bytes, we push and we pop 16 bytes. Sure. Pop below top. That seems weird, to be honest. Because we're basically throwing away the 42, you know. So this basically corresponds to this. We've called ourselves recursively, and we should just return that. So this returns an int. What, we push 64 from stack 8. That is weird. That is super, super weird. I mean, let's just do that, I guess. It's not gonna work, I think, but yeah, skipping the top 8 and popping the 16 below, jumping to here, pushing the last thing again, removing 15 bytes below that and 17 bytes below that, and then returning. And yeah, okay, so we've returned an address. That's not correct. I think this should actually be after calling a function. After calling ourselves, why is the offset 8? I would have assumed that the offset should be 0 here. Strange. Very strange. How are calls handled here? Ah, yeah. And then Waffle to byte code. I don't get it. Well, okay. Like, I think in general this looks pretty cool. That's at least something. Yeah, I should align the stack, and that's something we need to do anyway, and it also makes things a bit clearer, I think. So yeah, padding will be builder.align to 8. So yeah, we unbox something, copy data from the heap. And in the end, we just have this padding. Yeah, we need to, we've copied data from the heap. Yeah. Okay. Copy the data from the heap. In the end, we need to pop some things below the top. So yeah, data start is builder dot stack size, I guess. And then we need to do builder dot emit top below top. So basically we skip the top something bytes, like expression.size bytes, and we pop the padding bytes below. Yeah. Okay. Yeah, we also need to deal with alignment in here. So we need to make sure that when we push a pointer here, we want to be aligned to 8 bytes. So we're also gonna have to add some padding, which will be builder.align to 8. Yeah, we've loaded a single byte. And then we can do bytecode instruction top below top of, oh, what is it? It's like a couple, skip the top byte and then yeah, pop the padding below that. Something like this. Okay, so we do handle alignment, and I think I'm gonna copy this loop up here to make it a bit more simple, a bit simpler. If the cursor equals the expression size, then we are done. In other words, if the cursor is cursor minus 1 is less than the expression size. I'm going to leave it like this. But this one up here needs to have something like that. So, you know, if cursor plus 8 would be greater, yeah, really greater than the expression size, then we break. Otherwise, we know that we are aligned to 8 bytes. So we don't need to align that and underline the stack, but instead we can just push the pointer, push the cursor, add those, and then load 8 bytes at once, basically. Oh, but this also means that the object in memory has to be aligned, I think. Yeah. To do alignment. But this is going to make the code a lot shorter. Yeah. Yeah, because now we just push the pointer, we add a 0, and then we load the data at that pointer, but 8 bytes at once. And then we push the pointer again, add 8, and then load the data at that point. Then we push the pointer again, add 16, yeah, and then only load a single byte from there. Yeah, that makes sense. Oh man, okay. So then we have this is basically the loading. Now, we have a switch. Yeah, we get the pointer. Okay, so here the only thing remaining on the stack is the pointer. Okay. And then push 64 from stack. Yeah, then we load that content. We call ourselves. Yeah, we should have like consumed this, I think. Oh, but wait, after loading, we also want to pop this part, the pointer itself. That shouldn't be there anymore. Yeah. So compute the pointer to be unboxed. We've aligned the padding. We compute the pointer, adding, like effectively adding 8 bytes to our stack. Then here we have the data stack, and we load all that crazy stuff. And then here we pop the padding, but we also need to pop the pointer. So 8 plus that padding. Let's see. Oh yes, so now we have this right here. So that we basically, where's that? Here we have that call of unbox 17, and that is like a lot of stuff. We need to get the argument in here. We need to put that on the stack, some part of that at least. And the way we do that is we push that in the switch case. Yeah, the way we do that is we push that thing on the stack, extract the pointer, then load stuff from that pointer, and then remove the pointer, so that the only thing remaining on the stack is that loaded enum. Yeah, then we call something else. Yes, and then we say, please push the top element from the stack at offset 0. Pop the 8 below that. I'm not actually sure what that is about. That is about whatever happens before this. Yeah, no, that's not. Oh yeah, the padding apparently. Interesting. Okay, yeah. Push 64 from stack. Yeah. I'm sure it's gonna work. Whew. Okay. Yeah. Let me take a quick break. Okay. Right. What to do next is the question. I could try running this. Like, that would be cool, right? So I guess this main.call. And we call the main function, which doesn't exist, right? Because that's the byte code. Where does that? We have bytecode. That is just an address or something. We call that with 0. Oh man. I don't even know what's gonna happen. It's gonna segfold or something. Whoa. Yes, yes it does. Amazing. Why though? And what even is this? Like, huh? Push ping 500. Whoa, wait, what? 500? That's not what. I mean, this looks fine, I think. So we have a data stack of 8 bytes. We say, please push the top byte again. Okay, sure. You know what, let's maybe print the data stack like I did. Like I did somewhere. Here. Like having these things below each other, and I think that's cool. So, and that makes debugging easier. Like that's the main takeaway from working on compilers. Just invest in tooling, invest in having good stringification stuff, invest in, you know, building things that make debugging easier. We do have the heap now. Okay, so I guess let's just the right. Oh, hang on, no, the right function of the VM. That's what we're going after. Oh hell yeah! So here we have the data stack, and let's maybe have a cursor. Yeah. Yeah, let's do this. If I divides 8, then we write a new line, and in any case we write the byte which we get from the data stack. Can't type today. Okay, yeah, that seems correct. Should be ready to abort this. No, too slow. Okay. And that didn't change anything. Wait, what? Data stack something. Oh wait, we don't actually print the VM using the VM print call, I think. Well. Well, that's interesting. So then what do we print? Oh, we just do something. Oh, but this is cool. This is actually cool. Oh yeah, and also padded left. I like that. I guess. So standard out dot write the VM, please. And the VM should also be written using this nice syntax. Okay. Curious how this is gonna look. Okay. Okay, that is much cleaner. Also a lot more scrolling, but sure. Okay, so we start with this stack. All zeros. Alright, sure. So then we run this, pushing same number again. Sure. We call the function. Oh, this is probably the function that creates a list, right? Oh, and maybe there's a bug in that. Yeah, that may actually be, because we haven't debugged that a lot. So we push a byte, a single byte. That's cool. And then padding afterwards. Okay, yeah. And then we push that same number thing again, I guess. And then a byte. And that same byte again. And then padding. Interesting. Really interesting. And weird. But okay. Then we push that thing again, push some byte, push some other byte, and we run call. Okay, sure. So this is like gonna call a function, right? Like this is maybe casting this thing to something. I don't know. Okay, but what we do is we get the int, I guess, from inside of that. Ah, you know what? Let's maybe put something interesting in here. So let's put like not this in here, but instead, I don't even know, threes maybe. Yeah, some threes, like 1, 2, 3, 4, 5, 6, 7, 8. That's an interesting number to put in a list, I think. Oh yeah. Oh, that is pain. Sure. Not at all verbose. Oh, any sort of bounds is something we get. Okay, so we actually like caught an error or something. Ooh, let's see what happens here. Ooh, dang. This is interesting. Really interesting. Let's see. So we are like, hey, please create a list using that, because I think that's what let's maybe double check that. Yeah, the test plum accepts an A and then creates a list using that A. The A is an int and should be on the stack. On our stack we pass this whatever number that is, which is always 33 in hexadecimal. And the first thing we do is we push that int to the stack again, and then we call some function. What do we call? Well, probably we can even look at that up here. How we call the list function, the list that accepts the input int. I'm just looking at the list function. This will first create the tag, I think, or create the inner node being an empty thing of size 1, and then we'll create the outer list node, which will be, well, it will contain the int that we passed in as the payload, then the 1 from here, and then a tag around that telling us this is the more item. And then we cast that specific thing to the more general list type, which will then switch on things and do more complicated stuff. Okay, so we call this list constructor. The list constructor expects an int on the stack, and it will then push a list to the stack. It will consume that and push a list. That's the idea. So we run push 8. So far, so good. Well, this is like creating the empty list node. Just a single byte being the tag. Then we have padding, sure. And now we want to create the outer list node, which will be, well, the memory layout will be the int that was passed in, correct. Then the inner node, which will be the empty node. And then the outer node being something, like also a tag. And these are still the specific enums, each with only one variant. So both tags are 0. And then we push padding, and we call, we don't call something, okay. We want to call the casting function to cast that specific list into a more general list. But to do that, well, we're gonna have to we first push the argument to the stack again, because of course, the list is 2 bytes long, 2 words long, 16 bytes long. So we first push this first thingy, and then the first tag, okay, and then the second tag, sure. And then we run call. So now on the top of the stack there's a list of more containing an int and a list of empty. So the first thing we do is we push padding, I guess. Okay, let's actually look what the cast function is going to do. It is this one. So it accepts the 0 and it takes that, and at offset 9, the byte, so the last byte of this, basically tells us which variant this is. And for the outer enum there is only one variant, only the more. So not much of a switch actually. But we will do this. We will cast that int to an int. So we'll call some other function using the int at offset 0 size 8 from this argument. Then we'll call the empty thing, and then we'll create the list node and actually allocate memory for the inner list node. Okay, let's see how that looks down here. We do this call. So on the top of that is the very specific enums for the list node. We push padding, and the first thing we want to do is cast the int to an int, which should be no op. So we push the int to the stack. Okay, for some reason we do that again, like sure. Oh yeah, right. We basically switch on that. We want to switch on that input that we get on this input. So we add padding, and then first we push that input to the stack again. So we push this first the 3, and then the first tag, and then the second tag. Fair. And then we keep the last byte of that. and push 9 bytes before that. So basically this. That we have, 00 a, like this is the argument to our function, and then this is the tag that we want to switch on. Exactly. So we do jump table. Nice. And yeah, that consumes that byte, and we're now at some other place. The only possible place, which is first going to convert the the number. So it's going to push the entire stack thing first, aka the number and the tag and the other tag, and then it's going to pop the first 2 tags, so that only the number remains. It runs the cast function, it calls that. So now the cast function pushes that integer to the stack again, and then keeps that integer, those 8 bytes, and pops the 8 bytes below that, because now they've been transformed into an int, of course. Yeah, sure. So we have that, and then we return from that function. So the integer has now been cast to the integer of the other payload type thingy. Next, casting the empty enum. So again, we first copy the entire value of this one, and then the first tag, and then the second tag. And now we want this tag right here, the inner enum, being the empty enum. So we pop the top tag, and then we pop 8 bytes below that. So this is the integer that was cast, and now we want to cast this into an empty enum. Like currently this is just the enum only containing the empty variant with no payloads, and we want to convert that to the list type. So we call the cast function for that. The cast function is gonna push them, push the tag again. It's gonna switch on that, and oh, lo and behold, it's like there's only one possible tag. Ooh, push padding 16. That looks wrong. Interesting. Running jump table of something. Okay. Push padding. Like, when would you ever need push padding 16? Weird. Okay, so let's just look at what it does. So it pushes the byte, okay, and then pushes some padding, and pushes more padding, then pushes even more padding. It pops some things. Okay. I mean, maybe I'm just not, let's maybe cast, turn that into log txt, I don't know. How do we do eprintf or I think standard out, right? So this should work. Yeah. Okay, that's pretty cool. So we were currently in this, like we have done this, and now we run this function. Oh yeah, okay, 16 bytes of padding does actually make sense sometimes, like in here, for example. Oh, I see. Okay, so let's maybe open the log. Oh yeah, it's here. push padding 16. Yes. So what happened before? We ran the jump table. Okay, so we switched on this tag. And now we want to construct the enum. Yeah, and that's actually correct. Like, this doesn't have to be aligned to 8 bytes, because like you will never access an int from this, because this is just padding. So this is actually like correct. Crazy. Okay, so then what do? We have the padding and we have the byte, the 0. Running push 8, 0. Perfect. And yeah, I think then we just want to return that. So obviously we copy that to the stack, aka we first copy this byte, like these 8 bytes. Yeah, then the next 8 bytes, and then the byte. Beautiful. And then below the top something bytes, 17 bytes, we pop 17 bytes. Boom. Yeah. And then we jump out of the switch. Oh, and then we want to return that value, so we push that byte again, and again, the tag again, and then we pop below the top. We keep 17, and we pop 17, and then we keep 17, and we pop 1. So first this, and then we pop this one, resulting in this. And it actually looks fine. And we return from the function. So now the empty enum, which only consisted of 1 byte of the tag 0, got converted into this 16 bytes of padding and then the 0. So this we've successfully returned from this cast right here. And now we are here. And here's a box. So let's see how this is gonna go. So we've returned from this function. Okay. And we push padding, 7 bytes of padding, sure. Oh yeah, and now we build on the stack the new aggregate. So this contains the 1, which was the cast integer. Yeah, we have that here. Beautiful. And then we push the the cast, the empty thing. The 2. But now we actually want to, put that on the heap. We want to box that. So we push 64. Oh, yeah, now we want to allocate 17 bytes. So we do that. Oh. Yeah, we should add some padding there, some alignment actually. No. So we have 17 bytes, 17 as an int, yeah. And then alignment 8, so we also push an 8. And then we run malloc. And that actually like pops the 8 and pops the amount before, and it returns an address. That's crazy. That is super crazy. Damn. Okay. What? So then we push 8 bytes from the stack. Oh yeah, we push that same address again. We push 0, we add them, aka we do nothing to the address. And then we push the 8 at 1 byte from the stack at offset 32, this down here, the first byte of this payload. And we store that byte, which means we're going to consume that. Perfect. And it's now in memory. And then we repeat that thing. We push 64 from stack, we push 1, we add that, push the byte, store that. We push the address, boom, add that, repeat that. Repeat, 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 repeat. Store that. 11, 12, 13, 15, 16, store 8. And now this is interesting. So we add those, we store, we don't store that, hang on. Where am I? Byte number 15. Oh yeah, makes sense. We add that. Then we push, I think this byte here, and we store that. So then again we push the address again, we push 16 to the stack, we add that, we push 8 from the stack. That's interesting. Now this is the final byte, like this one, I'm not sure, one of these, and we store that, boom. So now we have an address. Literally just an address that tells us where the thing is stored. And then what do we do? Oh, like this is the... Is this already? Oh, pushing the byte. Yeah, no, that's not correct. So basically we want to have the number, like the int, and then only the address. Oh, we need to push pop the data below that address. Yeah. Okay, so let's fix that. And also the alignment, like boxing something should recompute the data to be boxed. Yeah, I think let's align the stack first. So that we can, copy 8 bytes at once. Makes sense. So padding will be builder align to 8. And yeah, we compute the data to be boxed. Then we need to padding before data. Padding after data is builder align to 8. Allocate memory for the data. Yes, please. And then copy the data to the heap. And that should work like this, actually. So if cursor plus 8 is larger than data.size, then we'll just break. otherwise we push pointer to the stack. We push the cursor, we add the cursor, we push data from the stack, emit the cursor, and then, yeah, down here when we are done, we actually need to emit bytecode instruction dot pop below top. Top 8 we're gonna keep because that's the pointer. Yeah, and then below that is the padding after data plus data dot size plus padding before data. Much shorter than the original. That's cool, I think. Oh yeah, because now we copy 8 bytes at once. Makes sense. Yeah, so let's maybe look for the malloc one. Perfect. Oh, look at this. We want to store this to the heap. So what we do is we want to allocate 17 bytes of data aligned by 8 bytes. Boom, here's your address. This time at a different address, which is totally fine. And yeah, then we push that address here. We run. Hang on, we push. Oh yeah, we just push a 0, we add that, resulting in that same address. We copy the first line, the first word from the data. We store that in memory. Boom. Then we push that pointer again. Then we push 8 and we add that so that the pointer is now, bigger. So F8 became 0, 0, and we have this overflowed into this. B5B became 5C. Yeah, we store the second run of bytes. Oh, hang on. That's interesting. Here, push 64 from stack. Okay, yeah, did that. Push 64, 8. Yeah. Adding those. Yeah. 40. That's like 40 is a big step. 16, 24. Yeah, 40 is up here. That is way too far. But where, hang on, where does that happen? Because up here, we pushed something from 32. That was fine. Oh, oh, I can probably see why. Now, as the cursor gets bigger, yeah, then this should get smaller, the offset. Or more intuitively, we do it like this. Yeah, that's way more intuitive. The data start plus cursor is basically the byte we want, or the word or byte we want to copy. Okay, so here we add them. We get that same thingy. Oh yeah, but now not 40, but 24. That seems more reasonable. So the second line of A's, we store that. Boom. Then we push that pointer again. We push a 16. We add those. Beautiful. And then we push this byte right here. 23 bytes get skipped, and that byte. Push that. And we store that byte. Beautiful. And now we pop below the top. We keep the top 8 bytes, aka the pointer, but we pop the 24 bytes below. Look at that. Our int and a pointer to memory. That's exactly what we want here. We have our int, then a pointer to memory, and then a byte that indicates the tag, the 1. And that's here as well. What? So this is actually like a linked list node, basically. Now we want to return that, I think. Yeah, we want to return that here. Oh, and here. Okay, so there's a lot of stack copying going on, probably. Yeah, pushing padding, sure. And then copying that thing over, so copying this, boom, copying 16 again, copying a byte, and then popping that same thing below. Okay, yeah, then jump, yeah, out of the switch. I mean, this is, damn, this, oh yeah, this removed all local variables from inside of the switch. So, damn, that's pretty cool. Yeah, pushing padding, of course. How is that correct? Let me just check that. Seems correct, I think, yeah. Okay, so we have padding, push 64 from stack, and again, and byte, and yeah, this looks correct, definitely. Now this is weird. We keep the top 17 bytes, this, but we pop 30 bytes below. 24, 30, yeah. Oh, I see. I mean, yeah, that's okay, I guess. So these are the arguments to the function, basically, to the list function, and this is the result we want to return. So then again, we keep the top 17 and we pop the 10 below. So this one, which means that our list function basically just consumed the value on the stack. The cast function, list function, I'm not actually sure. Our cast function, yeah. Our cast function consumed this thingy and replaced it with this cast value. And we return. Perfect. Then we want to return from the surrounding function, the list function here, after having cast this value. So what do? We do that same thing again. Pushing padding. Yeah, pushing padding. Yeah. Pushing a 64-bit thing from the stack. Yeah. Jump table. That is not correct. What's going on here? Why would we do that? Do we maybe just not have enough instructions, like, or like, in here maybe. Basically, if these are full, yeah, just, you know, to catch running out of memory there. I don't. Oh, actually, oh dang. That's crazy. Wait, but those are 500 instructions. How many instructions do we use? That's crazy. That is so crazy. Okay, so let's, I guess, just increase that, and yeah. What? What is like the first emit? Is there like a logic error in the check up here? And if these are equal, then really crazy. That is crazy. But we don't have 1024 instructions, do we? Yeah, what does reserve uninitialized do? Let's maybe look into that list. It returns a slice. It doesn't just reserve values, it also like removes the space from the list. I see. So I guess I mean, we could just do this. So still start emitting them at the beginning, I guess. And that did nothing. Hang on, that didn't crash. And it returned 42. Oh man. That is crazy. That's honestly crazy. What? That, I mean, that's amazing. What? debugging this was just a bit of pain, but also also pretty cool. Damn. What? We just have instructions here. That is crazy. Okay, so we can do like recursive functions, like recursive enums, and only if enums are recursive we actually allocate memory on the heap. And like in general we allocate memory, that is super nice. That is super nice. Let's maybe push that. So first of all, I guess this like fixes the instruction, fix emitting instructions or something. Yeah, then fix aggregate handling, and then the box and unbox things are new. That is amazing. That's honestly super cool. Crazy. Map offsets, okay, yeah, I don't know, some stuff down here. Yeah, this looks, oh yeah, this does not look reasonable. I should fix that. Yeah, memory layout. In our fun memory layout, yeah. I just want to turn that switch like this. Indent that. Dedent that. Yeah, because of structs. I mean, that's still an open question. Cool. Support recursive enums. Boom. Including memory allocation and stuff like that. That's super nice. I think this was like one of the most difficult parts of the compiler. Yeah. Until now. You know, who knows what's gonna happen. Okay, yeah, let's maybe I know, is there some other to-dos in here? Probably, right? Lambda. Oh yeah, lambdas. Lambdas. Yeah, the memory layouting of lambdas is still an open question, sure. Waffle to bytecode, is there also, like there, okay, that's fine. That's not so fine, hang on. For the waffle, is there, I like, yeah. Oh yeah, there were to-dos, lambda type. Yeah, and then lambda call. Oh, and instruction. Do I want to do this today? Is the question. I mean, what I did today was already pretty difficult and just texting, you know, so I think I'm gonna work on instructions a bit and then finish for today and do lambdas next time. Yeah. Okay, so yeah, instructions. And what does this even have? Waffle. Yeah, no, Waffle doesn't have any instructions. The yogurt has instructions. Yogurt. Yogurt instruction has a yogurt instruction, which has an instruction and arguments. Okay, so I guess arguments are yogurt IDs. Very similar to calls, I guess. Yeah. I mean, we're probably gonna do something like this, right? We have some instruction, means we get the instruction arguments, and then we get we prepare the things on the stack. Yeah, I know. Yeah, and then we just check on the waffle, like waffle. I don't know, switch on the instruction, basically. And let's maybe look in the built-ins. It can be any of these instructions, so yay. Okay, so when adding integers, we actually have like a waffle add 64 thingy that expects the arguments, right? And this will be a waffle sub 64 of the arguments. Can I do like a waffle 64 of the arguments? Yeah, I'm not sure what. Yeah, I mean, and an all and XOR and so on, they work the same way basically. Waffle crash, add sub muldiv mod and or XOR. Yeah, compare don't really exist. Should that exist? Maybe it should. I mean, oh, that's nice. So we don't actually need to do this. We can just do args is instruction.args. Yeah, we do need this mapping to yogurt IDs. Which is kind of sad. I mean, like this is pretty verbose. Mainly because of the long variable name, but still. That is a lot of stuff. A lot of code. Damn. I mean, I guess I'm gonna do that for now. Horrible copy paste. Like, this is honestly horrible code. Horrible code. Oh man. Yeah, concatenating strings. I don't know how to do that yet. Comparing numbers. Yeah, I don't know. Yeah, crash also takes 2 arguments, I think. Beautiful. Yeah. I mean, I guess that's it. That's the main part. And now we should be able to have the actual, like, this length implementation, not the stupid len. Let's see what happens here. Oh, and yeah, maybe not, like, you don't need to put that into the log.txt file, but yo, the list has a length of 1, that is correct. How about we put, I don't know, 1, 2, and 8 in there. Nice. I mean, that's pretty cool. Like, we allocate probably like 3 heap nodes or something, create a linked list, and then reverse that, dereferencing the heap pointers, and that's super nice. Okay, I'm happy. Like, this is pretty cool. Let's maybe commit this. Yeah, handle instructions. Oh yeah, let's maybe add something. Compare ins. Handle compare ins. And handle concatenate strings, which will be a whole other topic. Handle instructions. Beautiful. Okay. Cool. How many to-dos are there in this project, like in general? Oh damn, there was some. To do, yeah, relax. That's a nice thing. But it's about type constraints, not actually relaxing. No. Yeah, I think there's the most. There are still like some challenging things, like choosing memory layouts for lambdas and treating them correctly, and probably allocating stuff for captured variables and stuff like that. Yeah. But still, it's pretty nice. Pretty nice. Yeah, we have types, we have lambdas. We have crash arguments. Still need to do that. Sure. Oh, yeah. think here we can actually depend on the alignment, maybe. Like, yeah, that the pointer needs to be aligned to 8 bytes. But we may not be able to like get 8 bytes at once from the heap. If the data structure on the heap is only aligned by 4 bytes, then we need to get them out in groups of 4 bytes. Yeah. Oh, maybe one design thing, like one, I don't know. In the Waffle, we have these. Oh, that is much output. Too much output. Yeah. Let me just clear this and run this again, and then just scroll to the top. In the Waffle. Oh well. Oh, that's a lot of output. Okay, so I guess let's disable the printing, maybe. Yeah, standard OVM, maybe not a good idea. Okay, much better. Yeah, and in here, I like that we print the sizes in bytes, because bytes are basically everything you need. But in here, these are based on bits. I think that's kind of unfortunate. I mean, you don't... Yeah, like, it's more common to talk about 64-bit integers than 8 bytes. 8-byte integers, I guess. But still, I think it makes sense to put... have these instructions named after the amount of bytes they take, rather than the amount of bits. Oh, well, I mean, that means that code that used push 8 will now use this other variant. Let me do this in 2 stages, maybe push all the push 8 things and store 8 and so on, turning those into 1s. Yeah, and that will result in some errors, which is totally fine. Yeah. Okay, so that's the first thing. And in the Waffle, is there nothing? Does this compile? No. Yeah, I was just about to say that we have to admit those bytes, those instructions somewhere. Yeah, load 8 is not a variant, that's true. Beautiful. In the VM, there's still stuff in here. Indeed. Push And then the second stage, the second part of this change is changing the 64 suffix to 8. And same here. And probably, maybe here? No, not really actually. I think that's it. There's not a variant one. There is at 8, yeah. Yeah, that is a variant. Waffle bytecode. So we expressional kind. Oh, that's a waffle expression. Oh, the waffle expression has these as well. The bit width, basically. Oh, indeed, it has. That is. Do we need that? Maybe we still have the sizes and so on. I think it's, yeah, it's even fair. Like if you have, if at some point we have 32-bit integers and 64-bit integers, they could even use the same waffle expression, because and let the size determine like what kind of bit width thing that is. We don't need to highlight that in the instruction. Oh yeah, and in all our keywords, of course. Yeah, I know. Okay, yeah, it's probably gonna fail somewhere, right? Yeah. Waffle to bytecode, sure. Oh yeah. Just remove all the. Hang on. All the suffixes in here get removed. Something like this. Yeah. Nice. Yeah, I like that. Push 8 from stack. Yeah, that's a lot more intuitive, I think. So let's do that, push that as well. Use byte width instead of bit width. Consistently use byte width instead of bit width. Seems fair, I think. Okay, yeah, are there some other like minor refactorings I want to do? Oh, yeah, I thought about splitting up the code into separate files. Like, for the waffle, we have this right here. Basically, just the definition of the waffle, and then a lot of constructors and writing waffle things, and after that comes basically the converting yogurt to waffle part. And maybe it makes sense to put that into a separate file. And basically the same for other compiler stages, have one file that only contains the data, basically, like in here the bacon, for example. Then have a separate file for code or string to data, string to bacon. And the toast file should not contain the parser, but just the toast definition. Which, yeah, you see that's already like 200 lines of code. That's already quite a lot. And have the parsing and the conversion parts separate from that. I'm not sure if that really makes sense for all stages, like if it's really necessary, but I mean in this case, for example, the bytecode is like very tightly bound to the VM. So really the bytecode belongs to that VM. It doesn't make sense to group the bytecode together with the code that compiles to the bytecode, I think. And this is already this is a nice self-contained file, I think. It doesn't make sense to have some Waffle thing in here as well. So here I have the separate file. Yeah, I think it makes sense to do that for other stages as well, especially because we might also have optimization passes later on that take some compiler stage and emit that same compiler stage again. So basically Waffle to Waffle, for example. And yeah, that doesn't make sense at all. You know, those files, they would get bigger and bigger and bigger. It makes sense, I think, to factor out the conversion into separate files. So yeah, let me do that. Yeah. Yeah. Cool. Yeah. That is pretty cool. So I like how this turns out. Like, this is a nice tight VM. Optimizations are definitely like, we should do them. But still, pretty cool. Okay, so I'm gonna stop here, and I guess see you next time.